and the chair of this session. While he was in IMD, he was again the founder of numerical weather prediction. And today we can't think of weather forecasting without NWP. And that point in time, there was, nobody was willing to touch the NWP products. So Dr. Datta gave a good shape to the numerical weather prediction modeling. And also when the National Center for Medium Range Weather Forecasting was set up, he was given the responsibility to steer it, and he did it remarkably well. And so also the Indian Meteorological Society, he did a real good job. Today we have a very huge platform, and I think Dr. Datta made a significant contribution to that. So my salute to him. I'm sure he will be able to join us in between. Today's session is very, very important session, and we have three really very eminent speakers. And the session also, the topics of their talks today are very current and the vibrant and the frontier line research, I must say that. And in today's session, I would first invite Dr. Bhupendranath Goswami. I call him Bhupendra with my love and affection, our senior. Dr. Bhupendra was born in 1950 at Patbaushi, a small village in Barpeta district of northeastern Indian state of Assam, and come from a very humble rural background, and really took science of meteorology and atmospheric sciences to a very high level. And because the early schooling was really in rural settings, and so also many of us. He graduated in science from Cotton College, Guwahati in 1969, and then obtained master's degree in physics and PhD again in 1976 from Gujarat University while working at Physical Research Laboratory. And so our two eminent scientists, Sunil Kumar Singh and Dr. BNG, are from PRL. And then he took a postdoc from Cambridge MIT Institute during 78 to 80 and worked in NASA Goddard Space Flight Research Center for more than 3 years, and really made a significant contribution there. And thereafter, he came to Indian Institute of Science, Bangalore, and continued there till 2006, made significant contribution in understanding the monsoon. And then at that point in time, he was given responsibility to steer the Indian Institute of Tropical Meteorology, and really headed a very ambitious program of Ministry of Earth Sciences known as the Monsoon Mission Program, which started in 2009. And even after retirement from IITM, where he moved to IISER, Pune, to hold the MOES Sharoti Chair Professor, and worked there till 2015. And he's a known researcher, and particularly on the aspects related to Indian monsoon dynamics and predictability, and published very tons of papers, I must say. And he's very well recognized in the entire community, awardee of Shanti Swarup Bhatnagar's award, and which is award beside many other awards. So there's a huge long list, and I would really invite Dr. Bhupendra to deliver this talk. Dr. Bhupendra, floor is yours.
Thank you, Dr. Rathore. Thank you for those nice words.
Sir, Datta Sahab joined.
Some echo is going on. What?
Dr. Rathore, I am also checked in. Are you able to listen to me?
Yeah,
yes, we are able to listen to you.
Okay, fine. Let us listen to the Dr. Goswami, then I'll talk. Naturally.
Thank you.
Okay.
All the best.
Okay, thank you. Some echo is going on.
Sir, it's
Dr. Datta, you have to mute yourself.
Datta.
Okay. Okay. So thank you, Dr. Rathor, and thank you so much for those kind words. And good morning to all of you. This is a great pleasure for me to be here talking to you about some of the things that we have been doing. Let me first share my presentation. Okay, is it visible? Is the presentation?
Yes, it is visible.
Okay, I'll make it full screen. Okay. So I'm going to talk about a issue which has been bothering us for some time. For a long time, we have the prediction. Of course, the monsoon is a very important problem. It affects our agricultural production and food security, and droughts and floods really influence the monsoon significantly, and therefore it affects all of us. And as a result, the prediction of monsoon has been attempted for over a century today. And IMD was set up in 1875 with a distinct focus on actually making a prediction of monsoon. And Blanford was inducted to do that job, and he started looking for predictors around the world, and found correlation between monsoon rainfall and Himalayan snow, the first kind of predictor. Then, of course, was followed by Walker, who did very extensive studies of how different global parameters correlate with monsoon. And thus started the quest for predicting the monsoon. And over 100 years, starting from Gilbert time, over 100 nearly century, El Nino and Southern Oscillation has remained the single most dominant predictable driver of the monsoon. And that has happened because there is association of monsoon and El Nino. As this figure shows, that many of the El Ninos are associated with droughts and below normal conditions, while many of the La Ninas are associated with above normal or flood conditions. However, this relationship is not very exact, and it is rather, and particularly this correlation during the recent times has become very weak. At some point, for many decades, this correlation used to be rather strong, and therefore there was this sense that this is the major driver. But even today, however, as I am going to, that is my main issue, is that even today we are depending on El Nino for our prediction, and that needs to change. And that is my theme of the and I'd like to show that why we need to change that, and what are the bases for scientific basis, and how we can move forward, going beyond this El Nino based prediction and predictability of monsoon. So it has been shown as a spin-off of the Indian monsoon mission program, as Dr. Rathor mentioned, that the predictability of monsoon is much higher than we thought before. In fact, Sani and Shukla had done an initial estimate of predictability by doing signal to noise ratio, and monsoon signal, climate signal, appears to be above noise, and therefore it is predictable. But at that point of time, we really did not know how predictable it is. And that estimate was not available, and our estimate has evolved over the period of time. And today using a spin-off of the improved models and estimate of predictability with improved models, it is now known that the predictability of monsoon is much higher. And in fact, the seasonal prediction can, a potential scale, or the limit of the scale could be as high as 70% of the internal variability of monsoon. And and this has come as a result of this monsoon mission, this estimate. This is, I think, this is a major breakthrough in our understanding of how predictable the monsoon is. This has come from India's monsoon mission project. And I must say a couple of words in this the monsoon mission project. I must thank the MOES. The previous administration of MOES led by Dr. Shailesh Nayak, who had the vision to implement this ambitious program and did a extensive hard work to get all the logistics set in place, like the approval for the high performance computer from the model government, the approval for collaboration under the international funding mechanism from Ministry of External Affairs, etc. So there is a lot of hard work has gone and a lot of planning. And I was fortunate to lead this program to that extent. And therefore, I feel that we should acknowledge the contribution of Dr. Shailesh Nayak in these efforts. Unfortunately, I don't see that happening, and I wish that happens. So, having said that, let me go to the science. So the predictability of monsoon is much higher than can be explained by ENSO. The ENSO explains only about 10% or 20% of the variance, but we should be able to predict 70% of the variance and then where does the extra predictability comes from? And this is where so ENSO actually cannot explain the potential predictability of ISMR. And there is serious need that we need to go beyond and so to embrace other potential predictable drivers in the framework of ISMR predictability. Of course, there are several drivers that have emerged in the recent years, but unfortunately, these drivers are all, the correlation between their association with monsoon is relatively weak, even weaker sometimes than the ENSO. And but in the present context, since ENSO is still weak, and some of these drivers can become still large, but therefore we have to see how these drivers or identify if there is any other driver which is as comparable to ENSO or larger than ENSO in fact. However, over the last 40 decades, ENSO has dominated our understanding or prediction and predictability of the tropical climate is dominated by the ENSO concept and related to what is known as tropical ocean and global atmospheric paradigm. So as the ENSO became known slowly, ENSO became the dynamics of ENSO and this coupled ocean atmosphere interaction became clearer to us. The concept of tropical ocean affecting the global atmosphere became the basis for our predictability. And this remained, as a result, ENSO remained the single most story. And we refused to look at other things. And that has been a serious problem. So what is the toga paradigm? Let me go through a quick explanation of what is the toga. Toga actually started with the discovery that many of the tropical variability is strongly connected with extratropical climate, like the ENSO SST or rainfall over the equatorial region are strongly correlated with climate all the way to the polar regions. And this is through pattern known as Pacific North American pattern. And this was discovered from observation by Hall and Wallace. Then, of course, it went against some of the ideas at that point of time, because we knew that the waves in the equatorial region are embedded in the easterlies, and these easterlies they get trapped. And how do they go and affect the extratropics? So there is a conceptual barrier. But this conceptual barrier was removed or explained when Hoskins and Corley showed that the response of a heat source here can actually propagate to extratropics under weakly varying mean flow and long waves associated. If the heat source produces long waves, long planetary waves, those long waves can propagate into a slowly varying medium. So therefore, the conceptual basis of how tropics can affect the extratropics also became established. Having established that, people have really looked at and made this as a strong paradigm that, okay, the extratropical predictability is always very small, climate predictability. Therefore, the tropics can help them, and therefore, a lot of studies started looking at how tropics actually affect the extratropics. And many different studies have come up with conceptual framework of how this happens. And it was shown that even the extratropical, southern hemispheric extratropical climate is also affected by ENSO in this manner. David Corley had shown that this similar kind of teleconnection can be seen in the southern hemisphere as well. So with that, the TOGA became a very, very important program, but there are a lot of gaps because there are not enough observations, not enough modeling studies to understand the coupled ocean atmosphere. So the TOGA program became a real program of the WCRP, and it was launched in 1985 for 10 years. And it tried to determine the predictability of the coupled ocean atmosphere system on seasonal to internal time scale. Now, it affected, it sort of the strength of this program was that it affected all these three fields, observations, theory, and modeling in a coherent program. And it was a phenomenal success. And there is a lot of literature on that. So I don't want to go into. Most importantly, it improved the observing system, the Mood Boy program, after TOGA, the Cliver was had put during Cliver these floats.
Okay,
So
we'll push,
how
but
much time? I'll do. Okay. So we're able to show that actually the North Atlantic SST leads North Atlantic, the vorticity at the North Atlantic leads the monsoon rainfall and the circulation in this region. Therefore, we can say safely that the North Atlantic is actually a driver rather than the slave of these. So we have also shown there is another worry that, okay, how does the SST in the North Atlantic actually produce the atmospheric response? And earlier it was thought that the SST in the North Atlantic, in the extratropic cannot produce atmospheric response. But we have shown now that indeed it can produce the barotropic vorticity, and the barotropic vorticity actually leads the SST evolution. SST leads the barotropic vorticity here. Therefore, SST is the driver of the barotropic vorticity, and that barotropic vorticity drives the wave train, and that drives the monsoon. So, so this is now a sort of well settled. So with this background, we can actually another thing that has developed, which I cannot go through at this point of time, is that the subseasonal variations, the synoptic activity, and the monsoon intraseasonal oscillation also contribute to the seasonal mean. And some of that is as I saw, the active and break spells are clustered by the AMO. Similarly, they are also clustered by the ENSO, and as a result, the variance of the synaptic activity seems to correlate with the ENSO, and therefore the contribution to the monsoon by the subseasonal oscillations also are a part of that is predictable. And this is a new understanding that has evolved. So with these two measure new understanding, we have to revise the paradigm of monsoon predictability. Earlier, we thought only tropical SST can influence the monsoon, and extratropical was not that. And we thought that all that fast processes, the climate noise, are all unpredictable. But now we know that this a part of this climate noise is also predictable. So therefore, we have two predictable drivers, two quite known predictable drivers, and a fraction of the climate noise, which may also be predictable. Therefore, the predictability of the monsoon can be, in principle, much higher. As a result, so we have a basis now to think that the predictability of the monsoon is much higher. But to achieve this, we need good models, and those models. So in conclusion, what I'll like to say is that the ISMR is actually much more predictable than we thought previously, and but Toga-centric monsoon predictability is inadequate to actually to explain the monsoon predictability. Therefore, needs to be revised, including extratropical drivers like the AMO. Statistics of the subseasonal fluctuations are found to be modulated by ENSO and AMO. It must also include the predictable part of this contribution of the subseasonal. So therefore, and it has turned out that the models are beginning to capture many of these. Both the AMO, the CVIP6 models are beginning to capture the AMO correctly. And with higher and higher resolution and better physics, the models are also coming out with better.
Hello, Anandan sir, can you hear me? This is Aniket here.
हेलो
राकेश जी अपना माइक थोड़ा सा म्यूट कीजिए. आपकी आवाज आ रही है वैसे, आपका वीडियो भी आ रहा है.
I was just testing. Okay, thank you.
Okay, it's आ रही है.
Okay, thank you.
Anandan sir, can you hear me?
Yeah, Aniket, I hope you are able to hear me. This is Anandan. Hello. 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 Yeah, you are able to hear me now? Okay. Only I just want to make sure my presentation goes through properly. So I just, yeah, it is there now. Okay, 1 second. I'll just see that point. I have to put share file only, no? Or it's okay, okay. That is what it shows something. Now you are able to see? You are able to see my presentation there? It has come in full screen? Oh, good. Then fine. Then it works out. I think that displays real time. Some of the what you can say the. Oh, very good. Okay, then fine. I think I am through. So I will come around 11:30 and sit. Okay. Correct. Yeah. Okay, fine. Yeah. So to take out the share, what is to be done? I think escape only. Yeah, yeah, it is there. Yeah. Yes. Yeah. Yeah, you can configure up to 11:30. You're free. 11:30. I have any presentations to go for.
Hello, Ganga Hall backup. समरेश भट्टाचार्य समरेश भट्टाचार्य जी को और कमरेश सीए इनको एक बार पैनलिस्ट में डाल दीजिए ना. हेलो गंगा हॉल बैकअप, कमरेश और कमरेश्वर और समरेश भट्टाचार्य, इन दोनों को एक बार पैनलिस्ट में डाल दीजिए, ये लोग चेक कर लेंगे अपना।
जी सर, जी सर। उसका वो लिंक रखना पड़ेगा। दूसरा लिंक दूसरे डिवाइस की भी आपने लॉगिन किया है?
Hello. Yeah, can you hear me?
Yes, sir.
Okay. So, but share button is not activated right now.
सर एक मिनट में शेयरिंग देता आपको सर।
हाँ, शेयर दे दीजिए, मैं एक बार जस्ट चेक कर लेता हूँ।
जी सर।
सर अभी मेरा शेयर तो कंटेंट नहीं हुआ है,
जी
शेयर
सर,
एक्टिवेट नहीं।
सर कीजिए सर, शेयर कीजिए।
So now it is okay?
Yes, sir. Can you sir full select, sir?
Okay.
Full screen, sir.
Full screen.
Yes, sir.
How to
नीचे सर देखिए, राइट जहाँ पे माइनस प्लस का नीचे कोने में वहाँ पे फुल स्क्रीन का ऑप्शन है सर।
कहाँ पे है?
राइट साइड में नीचे देखिए सर, नीचे
राइट साइड में नीचे।
यहाँ पे माइनस प्लस है ना, प्लस माइनस आ रहा है, उसके बगल में देखिए।
स्पीकर, ओके 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 ओके, कहाँ पे
जहाँ पे आपके 2 लिखा हुआ आ रहा है ना, उसका 1 2 जैसे पेज का नंबर आ रहा है ना, 2 लिखा हुआ उसके नीचे देखिए सर।
नहीं नहीं, वो हाँ ठीक है, अच्छा मीन्स पीपीटी से, हाँ दैट्स करेक्ट, ओके।
हाँ सर, तो ये फुल स्क्रीन
हाँ, now it's okay?
यस सर। नेक्स्ट है सर। यस
It's okay?
ओके ओके सर।
ओके ओके, थैंक यू।
ईमेल आईडी हेलो योर सर, बिल नंबर इज योर।
सर कैन आई
यस मैम, यस मैम। ओके सर, आई सेंड द व्हाट्सएप। ओके, शेयर स्क्रीन में।
कैन आई शेयर?
यस मैम।
शेयर शेयर जाके शेयर फाइल करना है क्या? हेलो,
यस यस मैम।
शेयर
हाँ, शेयर पे क्लिक कीजिए मैम।
शेयर पे जाना है
जी मैम।
एंड मेरा डेस्कटॉप पर है।
जी मैम, वहाँ से क्लिक करके डेस्कटॉप पे यहाँ पे
एक सेकेंड आई थिंक आई शुड गो टू शेयर
जी मैम।
ऑन लैपटॉप, पावरपॉइंट। हेलो, हाँ जी देखिए सर, अभी दिख रहा है आपको?
नहीं मैम, अभी
हेलो,
तो अभी नहीं दिखा मैम।
मैंने शेयर किया है।
नहीं मैम, अभी आया नहीं शेयर।
और इसे फुल स्क्रीन भी किया है।
नहीं मैम, नहीं, मेरे को कोई कर नहीं रहा मैम। जैसे अभी उनका सर का आपने देखा होगा ना, सर ने किया था शेयर, तो उनका दिख रहा था।
हाँ, तो देखिए अभी मैंने शेयर दबाया है।
शेयर नहीं मैम,
शेयर पावर पॉइंट प्रेजेंटेशन।
हाँ, आ गया थोड़ा आपका इंटरनेट मैम लगा स्लो है मैम, इंटरनेट ठीक कर लीजिए।
ये ठीक है सर?
जी मैम, जी मैम। नेक्स्ट कीजिए मैम।
ओके,
नेक्स्ट करना मैम, नेक्स्ट स्लाइड दिखाना।
ये स्लाइड का मूवमेंट।
जी यस यस मैम, ठीक है मैम।
ओके
ओके मैम।
तो मेरा नंबर 5वां है। आई एम ऑन 5th इन द लिस्ट।
जी जी मैम, मैंने चेक कर लिया।
तो मैं इसे ऐसे रख के 11:30 बजे को इसमें करेक्ट करूं?
या मैम ठीक है मैम, वीडियो अपनी ऑफ कर लीजिए।
हाँ, तो अभी सब कुछ ठीक है ना सर?
जी मैम।
तो आई कैन स्टॉप दिस वीडियो एंड ऑल्सो म्यूट।
ओके। राकेश जी, हेलो। हेलो राकेश जी, सर 11 से 12 था।
हेलो
सर आप भी अपनी ऑडियो वीडियो चेक करना चाह रहे हैं सर? हेलो
प्रेजेंटेशन।
जी। हेलो
तो शेयरिंग इज नॉट अनेबल्ड।
सर मैं देता हूँ आपको, दे जी सर, करें करें सर, आप करें, कर कीजिए सर। ये मैंने कर दिया। पॉज कर दिया। किसी ने नदी किसको भेज रहा है? सर इसको जो ये ऊपर इनेबल करके है ना सर, इसको इनेबल कर दीजिए। हाँ जी, फुल स्क्रीन करिए सर।
ओके
यस सर, सर फर्स्ट स्लाइड दिखाना सर, पहली स्लाइड दिखाना सर। ठीक है सर, ठीक है सर।
ओके
ओके सर, ओके।
ओके थैंक यू।
हेलो गंगा हॉल, मैं अनिकेत बोल रहा हूँ। एक बार प्रतिभा माने और अप्पा राव बीवी,
जी
इनको
सर।
भी पैनलिस्ट में डाल दीजिए।
पर और सर ये दो बार आ रहे हैं, डबल डबल
हाँ, आई थिंक वो दूसरे वाले को लाना है। आ,
ये दोनों दे दीजिए।
हाँ। थैंक यू।
एक मैं शेयरिंग देता मैम आपको। प्रतिभा मैम, हेलो। हेलो आपका रॉय, हेलो। हेलो आपका रॉय, रॉय। नेट चले गए यार फिर, अरे फिर चले गए नेट भाई। अरे फिर चले गए, तुम्हारा भी ले गया। हैं? कौन सा वाला है तुम्हारा? आठ वाला कौन सा है? 11 का तुम्हारा? मेरा 11 से आ रहा है।
हेलो आया मक्का रहो
कैसे हो रहा है भाई?
हेलो
हेलो। हेलो सर, ऊपर है सर।
हेलो
हेलो सर, आपको शेयरिंग, ये पीपीटी शेयरिंग सर। हेलो हेलो। ये शेयर स्क्रीन सर, योर स्क्रीन शेयर सर। ऊपर है सर। कोई बात नहीं। Sir, can you share your screen, sir?
Hello.
Hello.
Hello. I am Appa Rao.
Yes, sir.
Can you check my link?
ये खा लेना समोसा ले हेलो हेलो सर हेलो
Yeah.
सर शेयर स्क्रीन सर
Hello.
हेलो सर कैन यू शेयर स्क्रीन सर योर पीपीटी सर हेलो कैन यू शेयर स्क्रीन सर
Hello.
कैन यू शेयर स्क्रीन सर
Can you check my link?
Can you check my link?
सर आप अपनी पीपीटी शेयर करना सर वहाँ से पीपीटी शेयर करना सर अपनी
Pardon?
सर अपनी पीपीटी शेयर करना सर अपनी पीपीटी
Yeah, PPT. Do you put or shall I put?
your PPT share sir
I shall put.
सर एक लिंक को सर म्यूट कर दीजिए सर आपकी डबल ऑडियो डबल आ रही है सर तो आपने दो लिंक खोले हुए हैं सर एक को म्यूट कर दीजिए सर वन लिंक यू आर म्यूट सर हेलो पर सर मेरी ऑडियो सुनाई दे रही सर आपको हेलो
I am loading my presentation.
यस यस सर कैन यू शेयर सर स्क्रीन सर कैन
See,
शेयर
are you
स्क्रीन
getting now?
सर यस 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 सर कैन नेक्स्ट सर नेक्स्ट स्लाइड सर नेक्स्ट स्लाइड
One
सर
minute.
सर आप अपने लैपटॉप के माइक से ही बात कर लीजिए सर, हेडफोन हटा दीजिए। आपके साउंड आ रही है सर हमारी आपकी?
Yeah, I am seeing here.
अभी सर आप लैपटॉप के स्पीकर से ही बात कर लीजिए, अभी तक नहीं आई सर आपकी साउंड। सर नेक्स्ट स्लाइड सर।
Uh, is it coming okay?
ओके सर, बट सर वो माइक्रोफोन तो सर ऑन है, बट सर साउंड आ नहीं रहा है सर। रेजुलेशन नॉट गुड सर, लैपटॉप
Pardon?
रेजुलेशन नॉट, लैपटॉप रेजुलेशन नॉट गुड सर।
Yeah, well, all slides are going through, but only I am not seeing to the full extent.
रेजुलेशन सर, रेजुलेशन लैपटॉप रेजुलेशन नॉट गुड सर।
That can be corrected later on.
अभी रेजुलेशन
Is it?
सर प्लीज, सर प्लीज शेयर द स्क्रीन। यस सर, अलाउड। क्या हो गया? अभी वो सफाई का बात करते हैं और प्लस नहीं करते बोले मतलब साउंड गंदगी में पैदा होने के सारे पहले तो ठीक था, अब हो गया गंदगी वाला है, अब हो गया ज्यादा गंदे पड़ गया ना इकट्ठा इकट्ठा। तो लेगा नहीं बोलेगा भाई। Hello, Nagaraj. Hello, Mr. Nagaraj, Kamlesh. Hello. Hello.
Yes, sir.
सर आप वो कह रहे थे ना पीपीटी चेक करनी है आपको अपनी
This is Nagraj actually. Yeah, no. In the sense.
सर मैंने आपको शेयरिंग दे दी है चेक कर लीजिए
Okay. Okay. Okay.
सर आपका कौन से सेशन में है सर आपका
No, no, no. This is Apparav and Kameshwari madam is there. Both are working with me. I will share the PPT of Apparav. Yeah, his PPT is not visible to a great extent. Then I will share his paper, Apparav sir paper. It becomes nice for him actually. You just check once. Now it's already opening. He's a very senior person.
Okay.
It's coming now. It's fine.
Yes, sir.
Yeah, good resolution. It was the issue with the resolution.
Yes.
This I will take care and he will explain.
Yes. Okay, sir.
Thank you. Apparav sir has to pick now. Then he will become another nervous again.
And they're not used to this online.
Hello, Anandan sir. Hello, Anandan sir, can you hear me? Hello, Anandan sir. Hello, Anandan sir, can you hear me?
Dr. Ananda, Apar over here.
I think refer to all the methods and everything he did. I was able to link up much later. That also on the mobile. I linked up on my laptop, but I could do it on my mobile. So good, Dr. Rathod. Thank you.
Nice to see.
Dr. Singh, excellent talk, and Dr. Behra, wonderful. All the best. Thank you very much.
Thank you.
And organizer, thank you all.
Thank you, sir. Thank you.
Thank you.
Thank you
Hello,
very much,
sir.
sir, for all the speakers as well as our distinguished chairs. And
Hello.
really, it is a wonderful session we are watching on India, even from the Japan. Study what
Sir, can you hear? Just a second. Can you hear? Can you hear us? Hello. Hello, Anandan sir, can you hear me now? No, apparently your voice is not coming. Hello. Hello. Hello, sir. Can you hear us? Hello.
एक बार रिकनेक्ट कर लो डिस्कनेक्ट करके रिकनेक्ट समटाइम्स प्रॉब्लम सॉल्व
हेलो लोग के वहाँ पे भी नहीं है
किसी का भी नहीं आ रहा है ना,
Yes, sir.
Hello.
Joined again? Just a second, sir. I will tell the technical team to put you to as a. Hello, sir. I can hear you.
না আমার যেটু গৈ আছে কারণ অডিও গলে মানে ব্লু হৈ যায় তো স্যার।
Hello, Anand sir, can you hear me?
Hello. Hello.
Backup speaking.
Hello,
Anand sir, can you hear me? Hello. Yes, sir. Can you hear us from Ganga Hall? Anandan sir.
Muted है सर तो खुद तो muted है.
Hello, can you hear us?
microphone is selected. Microphone selected.
From Ganga Hall. Yeah, can you hear us from Ganga Hall?
No, उनको सुनाई नहीं दे रहा.
नहीं दे रहा.
उन्होंने कॉल किया था मेरे को.
Okay.
वो अपनी टेक्निकल टीम को बुला रहा है.
लेकिन आपको सुनाई दे रहा था?
नहीं, यहाँ का इशू नहीं है.
यहाँ से आपको बगल में सुनाई दे रहा? हेलो बोला?
हाँ.
सुनाई दिया?
यहाँ का इशू नहीं है.
Okay.
डिस्कनेक्ट.
वहाँ पे सुनाई दे रहा है ना हम लोग का. ओके.
कहाँ में? वहाँ.
मतलब हमारा फीड तो गए ऐसे.
अब मैं तो वहाँ पे.
आप कुछ बोलिए तो तब.
वहाँ पे सुना ना.
Hello, Himanshu here. Hello, Himanshu here. Hello, Himanshu here.
Hello. Hello. Hello.
Hello.
उसका कैसे प्रॉब्लम?
Hello, technical team. Is it audible from Ganga Hall?
Yes, sir. Hello. हाँ जी सर. हेलो. हेलो सर मेरी और. हेलो.
So we are not listening to anyone actually.
Yes, sir. आपने लिंक शेयर किया. हेलो. हाँ, जो आपने लिंक किए हैं उसमें कंफ्यूजन है.
इसका आवाज सुनाई दिया.
हेलो सर. सर मेरी ऑडियो आ रही है सर आपको?
देवव्रत শুনি আছা নেকি? हेलो.
हाँ जी सर मेरी ऑडियो आ रही है.
আহি আছে না? তোমাৰ আৱাজটো অহা নাই যে এবাৰ অন কৰাচোন মাইক্ৰোফোন. अच्छा व्यूअर है क्या तुम?
Hello, can you hear me?
No.
Hello, Gangahar.
No.
सर मेरे को तो आ रही है आपकी ऑडियो।
ये तो हमारा आवाज आ ही नहीं। एक बार प्रॉपरली लॉगिन करो,
फिर से लॉग आउट
हाँ लॉग आउट कर दो।
अंकित सर। हेलो।
Sir, shall we start this, sir, now?
Yeah.
Yeah. So on behalf of the organizing committee, we welcome you all to the technical session 4A on the day 3 of this Tropmet program. This technical session is on aerosol cloud precipitation interactions, and in this theme we have two technical sessions. One is today and another is tomorrow at the same time, same hall. So today's technical session will be chaired by Professor S. Ramchandran, and we are normally giving a very brief introduction of Professor S. Ramchandran. Professor S. Ramchandran is a senior professor at Physical Research Laboratory and working in the Space and Atmospheric Sciences group. He did his MSc and PhD in physics and also postdoc at Rutgers University in USA. Sir has more than 100 publications and several awards and recognitions, including the NASA Group Achievement Award and INSA Medal for Young Scientist. The research interest of Professor Ramchandran includes characterization of tropospheric and stratospheric aerosols, measurements and estimates of aerosol radiative effects, size-segregated aerosol chemical composition using aerosol mass spectrometry, and modeling and the radiative and climate impact of aerosol, characteristic of cloud aerosol in nano size range and aerosol cloud interaction, and also satellite-borne estimates of radiative forcing of aerosols. So Sir also will be giving a lead talk today at the beginning of the session. The lead talk title will be Aerosol and Monsoon Rainfall. And today, as a co-chair, we have Dr. Mukundo M. Gogoi, who is a senior scientist at Space Physics Laboratory of Vikram Sarabhai Space Center at Trivandrum. And just for information, Dr. Mukundo Gogoi did his PhD from Dibrugarh University, and then he was postdoc at Space Physics Laboratory. He is a very active and core member of the national project on aerosol radiative forcing and also a few international programs. His research interest includes aerosol meteorology, atmospheric pollution, air quality, atmospheric physics, air pollution studies, air pollution modeling. And Dr. Gogoi has more than 70 publications in international and national peer-reviewed journals. So with this brief introduction, I hand over this session to Professor Ramchandran and also Dr. Gogoi. Over to you, sir.
Okay, thank you very much. So can I start the presentation?
Yes, sir. It is coming nicely. You can start, sir. It's coming nicely.
Okay. Thank you very much for the kind invitation and the words. At the outset, I like to thank the organizers of Tropmet for inviting me to give this lead talk as well as to chair the session. In these times, it is indeed a very important topic on which we are going to spend the next 1.5 hours today. So the title of my talk is on aerosols and monsoon rainfall. I will begin with a brief introduction on aerosols, how rainfall, and then linkages between the two. Some of the results that we got a few years ago, and also some of the recent results which has implications on the monsoon rainfall, and then we'll finally summarize the talk. So the aerosols indirectly can affect the cloud radiative properties, their lifetimes, etc., as is which is mentioned as which is denoted as the aerosol indirect radiative effect. The aerosols that are present depending on the type, size, and nature can modify the optical properties and lifetimes of clouds. And when there are more absorbing aerosols that are present in the clouds, this can lead to a shrinking of the cloud droplets, or what we call as the burn-off of the clouds, and would reduce the precipitation. So with this brief introduction on aerosols, how they are connected to clouds, and then the rainfall, let us look at the complex phenomenon called as the Indian summer monsoon, which encompasses the wide variability over the spatial and temporal scales. And it also comprises interactions between land, ocean, which is covered on both sides by the Arabian Sea and Bay of Bengal, and the atmosphere. Of course, to this august audience, Indian summer monsoon rainfall we know is dependent on a variety of factors, which includes the SST, soil moisture, snow cover, ENSO, Indian Ocean Dipole, and is also governed by the internally driven atmospheric process that are caused by the monsoon intra-seasonal oscillations. And we know that the rainfall across the country during the summer monsoon season, which is June, July, August, September, exhibits large spatial, temporal, and intra-annual variations. On an average, in the last 200 years, the average all India summer monsoon rainfall has been around 850 millimeters or so. The spatial, temporal, and the intra-annual variations in the rainfall are clear in the two pictures that we are seeing for the year 2002 and 2003 as a function of month, as a function of region. 2002, the rainfall amount was lower when compared to 2003, which was supposed to be a normal to an excess rainfall year. So there is also a large spatial variation in the rainfall. The rainfall over the northeast region, which is the dark blue here, is a factor of 2 higher than northwest, where I am residing. So the rainfall patterns are homogeneous across the 6 homogeneous rainfall zones. The moment we call homogeneous, these are based on similarity in the rainfall characteristics and association of the subdivisional monsoon rainfall with the regional and the global circulation parameters. And as was mentioned earlier, the June, July, August, September is the monsoon season, out of which more than 30% of the rainfall occurs or falls during the July month and can be considered as a core rainy month of the season. It also exhibits intra-annual variation, but more or less July, there is about 30 to more than 35% of rainfall that occurs. So we set out with an objective as to how the aerosols influence the monsoon on seasonal to intra-annual timescales. With this objective, we investigated the aerosol cloud characteristics in the rainfall patterns, the spatial and intra-annual variations over India for over a decade, which included drought, normal, and the excess rainfall years. So we used the MODIS data on aerosol optical depth, cloud effective radius, cloud optical thickness, columnar water vapor, and as a measure of the absorbing aerosol index, we used the total ozone mapping spectrometer, TOMS aerosol absorbing index, TRMM rainfall we have used, and the U and V winds from the ENSA pre-analysis. We have used the monthly average 1 degree by 1 degree latitude, longitude for the 11-year period, and the anomalies are calculated with respect to the 11-year mean. And we can see across the country there are about 450 grids, and each region, the homogeneous rainfall region, which we saw in the previous slide, it has about 80 grid points covering the entire latitude, longitude of each region, except for Northeast, which is a little smaller when compared to the other regions. So at the outset, let us focus on the 2 regions and also the All India, where we know that there is a big difference in the amount of rainfall between Northeast and Northwest, and also the All India pattern. So the values corresponding to the particular July of every year for the 11 years are plotted. The aerosol optical depth and the aerosol absorbing index on the left y-axis, and the rainfall on the right y-axis. So we can see that there are intra-annual variations across each region, and we can see that, for example, Northwest, the rainfall, which is in blue here, is significantly smaller when compared to the other years, and even all over India, this kind of the reduction in the rainfall is visible, while northeast, not much of this variation in terms of the rainfall is seen. With this background, let us look at the anomalies in each of them from the 11-year mean. So we can see that northeast, for example, be it the aerosol optical depth or the aerosol absorption index, and the rainfall is kind of normal to excess. But if we look at 2002, rainfall is very, very low over northeast, and we can see a consequent increase in the aerosol optical depth and the aerosol absorbing index, and which is true for the all-India regime also. So we also see internal variations over this region, but over all India, for example, these variations are significantly visible in 2002 as compared to the other years. So these the variations in the aerosol and the rainfall are also manifest in the cloud characteristics, which are the anomalies in the cloud effective radius and the cloud optical thickness, and the columnar water vapor, which is again a measure of the rainfall or the precipitation. So we can see that all the three parameters are lower during 2002 over northwest region, while not much of variation is seen in the northeast. And over all India also, we can see this variation in all the cloud characteristics also. So if we look at the 2 years, 2002 and 2003, the normal rainfall, which is shown as the red curve here. So the day-to-day variation in the amount of rainfall that occurs, and this is based on the 100 years of rainfall data across the country. And the years 2002 and 2003 rainfall every day between June 1st to September 30th are juxtaposed. And you can see that there is a large region in which there is a deficit, large time frame in which it is deficit during July, which was marked by what is called as the monsoon breaks, which is the intermittent stopping of rainfall that can last for about 4 to 20 days during this month. Based on the analysis for the last 30 years or so, in 2002, we see that this break lasted longer, almost for a month, for about 23 days, between 5 to 16th of July, and then followed by 20 to 30th of July. So during these days, when the rainfall, which is precipitation, which is one of the effective removal mechanism of the aerosol as a form of the wet removal, the drier conditions, the absence of rainfall, gives rise to dust and smoke, and then which a consequent increase in the columnar content of the aerosol, as well as in the absorbing component of the aerosol. So if you look at the 2 years, so the total, there was a deficit about 40% in the rainfall in 2002 as compared to an 8% excess or near normal during 2003. So these 2 years are years in contrast during the decade, which is one is marked by a drought conditions with a significant deficient rainfall, one with almost an excess to a normal monsoon rainfall. So these features are very clearly visible as a function of space and time. For 2003 and 2002, these are for July. Wind speeds, when the winds are from the Arabian Sea, are also plotted. The wind speeds are in excess of about 10 meters per second during the monsoon months across the region coming from the Arabian Sea. We can see that the 2002 July is marked by a huge increase in the optical depth, which we learned that it is because of the drier conditions that existed, and an equal increase in the absorbing aerosol characteristics also is visible when compared to 2003. So one of the other factors that could contribute to the variation in the aerosol characteristics across the Indian subcontinent is the winds that are coming from the Arabian Sea, the ocean surrounding the country. Depending on whether it is in the easterly or the westerly phase, this can moderate the aerosol characteristics across the country. But it has to be also noted that the sea salt component, which is maximum in the total optical depth during the monsoon season, it contributes less than 10% to the total optical depth. So almost all the optical depth, about 80% or more, is contributed by the other species that are present over during the time frame over the country, and also the transport of the mineral dust that occurs from the the arid regions that surround the western side of the country. So it is to be noted that in India during summer monsoon, non-sea salt aerosols dominate the column contribution. However, the surface level concentrations of sea salt particles could be different. So here we are looking at the columnar contribution, and so the influence of winds in modulating the aerosol characteristics on an yearly basis, on an inter-annual basis, is much less when compared to the other changes that we will see now in the next few minutes. So for the rain to occur, the precipitation to occur, the precipitation threshold cloud effective radius is presumed to be 14 micrometer. And so here we are looking at the cloud effective radius, the frequency of the cloud effective radius in percentage over Northeast, Northwest, and all India. And what is very clear is that over Northeast, where there was a deficiency of about 90% of the rainfall, maximum of almost 80% or so, the cloud effective radius fell within the 14 micrometer range, which means that the precipitation is going to be less. While all other years, you can see that the precipitation frequency is more than 14 micrometer, and which is seen in the other bins. And similar differences are seen across all India. While you can see in Northeast consistently, the values are greater than 18 micrometer or so, which is a definitive cause for the rainfall to occur more when compared to the other regions of the country. And 2002, for example, across the country, we can see that the 10 to 14 micrometer bins is contributing almost 30%, which led to a decrease of about 30% reduction in the all India rainfall. So the aerosol indirect effect, which is like the cloud effective radius decreasing because of the increase in the aerosol optical depth and also the absorbing component, which will result in a cloud effective radius decrease. So it's the observational evidence for this aerosol indirect effect to have occurred in the last decade or so. So one of the other important points that we need to investigate is that, is this analysis, is it uniform across the region? And so if you look at the correlation between the aerosol optical depth and the other cloud parameters, including the rainfall, we see that over the Northeast, for example, the AOD and the rainfall correlation is strongly positive, whereas the cloud effective radius and the rainfall is kind of low, the correlation. So due to a combination of variability in the meteorological conditions, the type of aerosols that is present over the Northeast, for example, which has abundant more amount of natural aerosols when compared to the other regions of the country, because it is the density, population density is significantly lower, and it's also abundant in terms of the natural aerosols, while the other regions, it is not the scenario. So this kind of inverse relation seem to have occurred due to what is called as the indirect effect that is caused by the heterogeneous ice nucleation. The correlations obtained over the homogeneous rainfall zones, which are larger, which are spatially large regimes. So we were also interested in seeing how this aerosol cloud rainfall interaction occurs on a grid by grid basis in each of these regions, which is shown in this transparency, where each of this 1 degree grid, we have shown the correlation between rainfall and the aerosol optical depth and the cloud effective radius and the aerosol optical depth. We see the patterns of agreement that are natural over the large space is also evident in the grid by grid analysis. So clearly suggesting that the natural patterns of correlation based on homogeneity in aerosol cloud and rainfall can be drawn by looking at by analyzing or examining the spatial pattern, larger spatial pattern, and the point by point or the grid by grid correlation captures well the correlations obtained on the larger spatial scales. So moving on to some of the recent results that we have obtained over the aerosol characteristics and the changes in the last 2 decades over the Asian subcontinent between South and East Asia. What is clearly visible is that just like the Indian Ocean dipole over the sea surface temperature, we are clearly seeing an Asian aerosol dipole because of the changes in the anthropogenic aerosol emissions. So the aerosol dipole is characterized by an increase in the South Asian region and a decrease in Southeast Asia, which both of them are the two global aerosol hotspots. So the decadal changes in the aerosol content, the loading in terms of AOD, which is shown here, as well as the composition, which we'll see in the next transparency, are visible. So the increases over the South Asian region are manifest in the differences that are shown here, while the decreases are shown in the East Asian region. So the model simulations of monsoon due to aerosol perturbation and the representation of precipitation are uncertain given the lag of or the representation of the aerosol emissions from the emission inventories across the region over this entire Asian region. So if you look at the point specific in situ ground based observations, and also the trends, those were based earlier were either based on model simulations. So the high quality observation based trend analysis is crucial to develop, as we know that any variation in the aerosol characteristics on a long term in terms of decade is going to have a significant influence on the aerosol cloud characteristics and the associated changes in the water content, hydrological cycle, etc. So if you look at the two locations, namely Kanpur and Beijing in South Asia, in the IGP and the North China Plain, in South Asia and East Asia. So the AOD dipole in the aerosol content is very clearly visible. There is an increase in the South Asian region, while there is a decrease in the East Asian region. And the decrease is more since 2010, because subsequent to the Olympic Games, which were held in Beijing in 2008, which turned to be a pivotal point in terms of starting to decrease the emissions. SSA, single scattering albedo, which is a measure of the aerosol absorption capacity, is also seen changing over time, and the aerosols have become more scattering in nature. So an increase in SSA could occur because of increase in the scattering aerosols and or accompanied with a decrease in the absorbing aerosols. A seasonal analysis of the aerosol characteristics also clearly showed that the variations in the content and the composition have occurred due to changes in the anthropogenic contribution and not due to changes in the natural. In fact, the natural aerosols, namely the dust and the sea salt concentrations, have either remained the same or show a declining tendency during the last 2 decades of observations. So the reasons for an increase in SSA over East Asia are the emissions of black carbon, which is an absorbing species, and also sulfur dioxide have decreased since 2010 because of the strict regulations in the emissions and the air quality norms. While for South Asia, the reduction, the increase in SSA occurred mainly due to the increase in sulfur dioxide emissions. The other major difference between these two regions, the East and the South Asia, also is shown in the fossil fuel contribution to the total BC. Black carbon, which is a resultant product of the incomplete conversion of fossil fuel, biomass and biofuel burning, the fossil fuel contribution is higher when compared over East Asia when compared to South Asia, which is 30 to 50% or so, while it is over East Asia, it is about 60 to 80%. So because of the decrease in the aerosol optical depth or increase in aerosol optical depth over the South Asia, accompanied with an increase in the single scattering albedo in both the regions, so we can see the aerosol induced heating rate has decreased over both the regions in the last 2 decades. However, it is even after 2 decades, it is still higher at 0.6 degree Kelvin per day in the only due to aerosols, which has significant climate implications. So the other major factor that could be contributing to the differences in terms of the loading and the absorption is that the black carbon dominates the aerosol absorption over South Asia. An analysis from across 11 sites across covering the South Asian, including the Himalayan foothills, we clearly see that the black carbon dominates aerosol absorption across the column concentration, contributing to more than 70% of black carbon to total AOD. Brown carbon, which is another light absorbing carbon and is co-emitted along with black carbon in all these fuel emissions. The contribution to AOD is higher over South than East Asia, which again confirms that the biomass burning emissions on aerosol absorption of South Asia is dominant, which is also seen in the earlier result where we found that the fossil fuel contribution is lower over South Asia when compared to East Asia. It's also interesting to know that the models, be it the global circulation models or the general circulation models and the global climate models and the chemical transport models, grossly underestimate the aerosol absorption by a factor of 2 to 10, mainly because of the absence of emission inventories on black carbon and brown carbon, which are beginning to come now. So this is another important point that is going to contribute to the changing aerosol effects on climate. So in summary, for example, the intraannual and spatial variations in aerosols, cloud and rainfall over India for more than a decade we analyzed, and then which included drought, normal and excess monsoon years. And we saw there were intraannual variability which were attributed to the conditions that existed in 2002, which was a drought year. And the anomalies were higher over India. Northeast India showed what is called as an inverse aerosol indirect effect, which is caused by the variation in aerosol types and also due to the homogeneous ice nucleation. And during the monsoon season, we also clearly saw that the non-sea salt aerosols are the ones which dominate the total AOD. The aerosol cloud rainfall linkages were more stronger during July, which is the core rainy month of the season. And the grid by grid analysis also, along with the spatial regional analysis, clearly revealed that these are natural patterns of correlation that exist, and then they agree in terms of the AOD, the cloud and rainfall and precipitation, thus providing the observational evidence for the indirect effect of aerosols. So we closed this presentation on the Asian aerosol dipole and its implication, which adds a layer of complexity, for example, to the already existing contribution of aerosols to the monsoon changes. So these diverging trends in the aerosol dipole of an increase in the aerosol optical depth accompanied with a decrease in the aerosol optical depth over the East Asian region, whether it will slow down or unmask the global warming because these aerosols are cooling the surface, which will result in large-scale changes in the regional atmospheric stability with implications on monsoon. This particular finding also becomes important because of the recent model simulations where we clearly saw that the shortwave absorption, which we saw in this, which is the aerosol induced heating rate, which is in excess of about 0.5 degree, can stabilize the lower atmospheric region and hence contributing to a decrease in the monsoon rainfall. So the impact of the Asian aerosol dipole and its associated effect on the diverging trends to climate change and the regional atmospheric stability and monsoon is the need of the hour that we need to do this. And with this, I would like to end my presentation and thank you very much for your attention.
Thank you very much, sir, for your very attractive and informative presentation. Can we take up a couple of questions now from the audience?
Sir, may I ask a question?
Yes. Yes.
Yeah, sir, this is Rohini from Pune University. Very nice informative talk, sir. It was really good results. I'm interested specifically for that aerosol-induced heating rate decreasing. So was it for a particular type of aerosol or for the overall AOD thing?
No, it's for the total overall AOD.
Okay, okay, sir.
Any other questions? Sir, can I ask a question?
Yes. Yes.
Yeah. The northeast region that you have shown that there is an increase in rainfall, means there is higher rainfall amount compared to the western part of the country, and that region, northeastern part, is topographically unique. That is in one way, and secondly, it is dominated by biomass burning aerosols, whether the western part is mostly dominated by dust aerosols. So in addition to topography, how much the effect of aerosols, biomass burning or dust, can we have an understanding on that thing from our scientific analysis, or can we have an approach on that thing?
Okay, so the only information that we need to deduce can actually come from the model results, because identifying the dust contribution from the observations, yes, they are available, but we don't have such data over the northeast region where we can, from the optical depth, where we can identify, segregate them to be biomass burning, and because the signatures of these, if you based on the aerosol metric, if you look at the either the absorption exponent or the extinction exponent or the fine mode fraction, there are the differences are actually very narrow. So they can, one of them can overlap on the other, and also a clear distinction can occur or can result in the model simulations. But as I pointed out, the emission inventories need to be strengthened over both the regions. Especially now with this, now we are seeing that either the dust has decreased or remained the same across the IGP, but it may not be true over the northeastern region. So these are contrasting things that we need to understand and kind of get the quantitative nature of it.
Yeah, thank you so much. So, if there is no other questions, then shall I proceed, sir? What do you say?
Yes. Yeah. Yeah. So I request Dr. Gogoi to conduct the session. I will be there, and so I hand over the mic to Dr. Gogoi.
Yeah, thank you. So we have 7 presentations in this session. And the first one is by Suvarna Fadnavis. And the title of the presentation is Elevated Aerosol Layer over South Asia versus the Indian Droughts. It's an interesting topic. So over to Dr. Fadnavis.
Is my screen shared now?
Not yet.
What should I do?
He will give the command. Just a second.
Yeah.
Unmute रखना बस वीडियो नीचे. Is the share button activated?
It's activated. I clicked at it.
Now first you open your PowerPoint, then click on the share button and then select your PowerPoint. It will come.
I have PowerPoint on in the background.
So once you click share, one icon opens, I mean one window opens. There you have to select that presentation, select that and then share.
Page on. It is not showing the PowerPoint here. When I open text, Microsoft text, I should do that.
It is coming.
Yeah, now it's coming.
It's a presentation?
No, it's as of now it is blank, but yeah, you might have to share the entire screen, I think, and then do the.
So I was a little bit confused how to do this. Stop sharing. Oh my God.
Stop sharing and again share, please.
Yeah, stop share and then do it. Share again. Once again.
So go to share contents. Let's say share. What is coming?
Yeah, it is. I think it will come.
Window is not open.
Yeah. But our screen mouse is visible, isn't it?
Yeah, are you able to see?
Sometimes this is happening because of some bandwidth issues. Madam, maybe you can stop your video.
Yeah.
Share.
Okay.
Yeah.
I stopped my video and now I share my content.
Yes.
So Microsoft Text, okay. I clicked on the presentation. I said share. So is it okay?
Yeah,
Now it's available. Yeah.
Available.
Yeah.
Okay, thank you. Okay, so today I'll present our paper which is recently published. It is on elevated aerosol layer over South Asia, which worsens the Indian drought. Here, aerosol layer means aerosol layer I'm talking about in the upper troposphere near the monsoon anticyclone. So recently, using number of model simulations, satellite data set, trajectory analysis shows that the emittents, means pollutants which are emitted at the surface, are lifted up by the monsoon convection up in the upper troposphere near the tropopause, and part of them are further transported into the lower stratosphere. This is a paper by Livid in 2018 appeared in Science, which says that monsoon is a big cleansing machine. It removes a lot of pollutants from the atmosphere by wet deposition. However, 1/3 of them are still managed to go up and they cross the tropopause and enter into the lower stratosphere. Another paper by Park et al. In 2008 nicely gave a schematic that this convective upliftment occur in the upper troposphere. Majority of these pollutants have their outflow around 12 kilometer and part of them are further transported up into the anticyclone and a form layer there in the monsoon anticyclone. Further studies by different groups have been made and this is a figure from trajectory analysis. Again, this analysis shows that the air mass which arises into the monsoon anticyclone has its sources majorly over South Asia and East Asia. So, monsoon convection the pollutants from the Asian boundary layer into the upper troposphere and they enter into the monsoon anticyclone. And the aerosols which are lifted up, they form a layer in the upper troposphere known as Asian tropopause aerosol layer, also referred as atoll. So atoll is also visible in calypso measurement. This is a figure from Vernier et al. 2015, and here we can see that there is a clear signature of aerosol layer around 14 to 18 kilometer residing over the Asian monsoon anticyclone region. We used Hammond's model and we see that our model also shows atoll, which I'll come to later. And we can see that it has majority of black carbon, organic carbon and sulfate, nitrate, all aerosols are there. Here I have shown the distribution of black carbon and organic carbon aerosol in the monsoon anticyclone. We have taken a measurement at Nainital in 2016 August, and we see that in everyday profile there is a signature of atoll in the upper troposphere at the Nainital. So, in order to understand the impact of this atoll, what are their sources, how it is formed, we used chemistry climate model, which is ECAM6 HAMOS. Here, ECAM is a general circulation model, HAM is a aerosol module, and MOS is a chemistry model which contains lot of gases. So we used a model at 1.8 by 1.8 horizontal resolution, and it extends from surface to around 18 kilometer. And we used ACMIP2 emission inventory. We performed basically two experiments, one with aerosol and one without aerosol. And we made simulation for El Nino year and non-El Nino years. This study, other than this model simulation, we have used Calypso satellite data, MODIS, MISR, etc. So when we started analyzing, we realized that on some of the days, some of the years, Atala is thicker and mostly concentrated over the Indian region, and while some other years, it is widespread over the monsoon anticyclone region. So we found that when El Nino years are associated with a thick Atala residing over the Indian region, and non-El Nino years, it is widespread within the monsoon anticyclone region. So figure here, we can see that Calypso observation also shows thick and concentrated atoll over the Indian region in 2015, and this is figure from ECAM 6 Hammers model simulation, and we can see that atoll is over the Indian region in El Nino year 2015, and while in 2016, which was a non-El Nino year, we can see that atoll is widespread over the monsoon anticyclone region, even in Calypso and in our model simulation. So we further analyze this, and this is the distribution of deforestation model simulation, and we can see that model shows atoll over the Indian region, and this is for the normal year, and this is for the El Nino simulation, and we see that during El Nino year, supply of aerosol majorly occur from the East Asia, which is then lifted up and enter into the monsoon anticyclone and form a thick atoll over the Indian region. This is distribution of black carbon aerosol, and we can see that first is for normal year, and D is for normal year, and E is for El Nino year. And we can see that in normal year there are two branches, one rising from South Asia and another rising from East Asia. But during El Nino, because of subsidence over the Indian region, South Asian branch becomes weak, and supply of aerosol to the monsoon anticyclone is majorly from the East Asia. And this East Asian branch supply aerosols to the monsoon anticyclone and form a thick atoll over the Indian region. This can be seen in this difference plot. D minus is F here, and we can see that atoll is thick and residing over the Indian region during the monsoon season. So we understand the impact of this atoll. So what we do, we took offline model, which just has a contribution coming from the aerosols in the UTLS, not throughout the troposphere. So these are the figures obtained from the offline model, and we can see that our offline model shows that these aerosols has produced significant cooling over northern India in the monsoon anticyclone region, and complete, these are the anomalies in solar flux at the surface, and we can see that Asian monsoon anticyclone region has a negative solar flux reaching at the surface. This aerosol in the upper troposphere has increased the stability in the upper troposphere or mid troposphere over the Indian region. And when we see the heating rate anomaly, we can see that over the Indian region, complete troposphere is cool because of this aerosols in the upper troposphere. Further, we analyze the impact of rainfall. This is a figure in rainfall anomaly without aerosols. When there are no aerosols in the model, and El Nino is controlled. This is done because we know that El Nino itself creates a monsoon deficit. So our model shows that this is the effect of El Nino. First figure is the effect of El Nino. So our model shows that El Nino itself creates a deficit rainfall over the Indian region. But when we switch on the aerosol in the model, so figure B is aerosol on El Nino minus climatology, and we can see that it further decreases the rainfall over the Indian region. So we say that this aerosols has enhanced the monsoon deficit around 17% over the Indian region. Here we show the schematic. This is aerosol layer in the troposphere, and then there is atoll in the normal year. In El Nino year, we have aerosols in the troposphere, and supply of aerosols in the atoll is higher and mostly from the East Asian region, and which then intrude over the Indian region and form a layer. And by the solar dimming, cooling of the troposphere, weakening of the monsoon Hadley circulation, decreasing the north-south temperature gradient, it further reduces the rainfall over India by 17%. So these are all conclusions. So we say that during El Nino year, aerosol supply mostly occurring from East Asia to the monsoon cyclone form a thick layer over the Indian region, which is concentrated over the Indian region, and it causes solar dimming. It causes a cooling of the troposphere, weakening of the monsoon Hadley circulation. It decreases the now temperature gradient, increases the stability of the upper troposphere, and eventually amplifies the El Nino related drought over the Indian region. That's what I want to say. Thank you.
Yeah. Thank you very much, Dr. Fadnavis. It's a very interesting work, and it is well within time. So we can take up one question from the audience.
Yes.
I have a question. The BC and the OC that you showed, they correspond to the mass, or what is the unit?
Nanogram per meter cube.
So it is a mass at the surface level.
At that level, UTLS level.
Oh, UTLS. And this
300 to 50 HPA.
And that was in the month of August or July? Which month was it?
It's a seasonal mean JJS, I think so.
Oh, okay. Okay. Thank you.
Okay, I have one question.
Yes.
In 15 to 18 kilometer altitude range, type of aerosols, especially sulfate or the carbonaceous, will have strong impact on this effect, like monsoon precipitation. Do you have any information regarding that thing?
Can you repeat? I was losing your voice. Can you repeat your?
Yeah, in that 15 to 18 kilometer altitude range, the sulfate or scattering type of aerosols and absorbing aerosols both will have different impact. Okay, so whatever you have shown today from the model simulations, which type of aerosols have maximum impact on the precipitation in that elevated, if they are present in that elevated layer?
I got your point. Yes, present study shows whole aerosol layer, but sulfate, nitrate, BC and OC will have different impact, and we need to do different simulations for each type of aerosols, and then we can see the contribution coming from each. But recently in 2000, I think recently 6 months ago, we published that sulfate aerosols has a more scattering type of aerosol being higher impact than other aerosol. But we have not seen the nitrate yet to say conclude anything on that.
Yeah. Thank you very much.
Thank you.
So, if there is no other questions, then shall we proceed to the next presentation, sir?
Yes.
So, next presentation is about power, and the type of the presentation is aerosol type induced changes in precipitation patterns over a tropical station, Pune, India. Over to Rohini Bhavar.
Is my screen visible?
Yes.
Okay. Yeah. So, good afternoon, everyone. I am Rohini Bhavar. I work as assistant professor in Department of Atmospheric and Space Sciences in Savitribai Phule Pune University. So, I'll be talking on aerosol types induced changes in precipitation patterns.
Please slideshow.
Make it a slideshow.
Yeah. Okay.
Yeah.
Over a tropical station, Pune, India. So we all have know that from previous studies that there is an increasing trend of aerosols over Indian region. The sources of aerosols, their transport, how they transform, and their renewal processes, it varies over different regions in India. And we also are very well aware that aerosols act as CCN, and they can affect the cloud microphysical properties, and hence the precipitation over the region. So our previous study in 2013, we have shown that presence of smoke aerosols, especially over the core Indian region, it reduces the cloud fraction by almost about 30% in a drought year as compared to a normal monsoon year, and hence it can initiate drought-like conditions, specifically in June and July months. We have also seen that Manoj et al. Paper, which is published in 2019, it shows a decrease in the surface black carbon concentrations over Indian region from different observations, station observations. And one reason what they have attributed to this decrease in the surface, especially black carbon concentration, is to the vertical redistribution. So hence, our main objective in this study was to demonstrate how different types of aerosols induce or impact the precipitation intensity. So the data which we have used in this study is for heavy precipitation events, we have used disdrometer data. Disdrometer is an instrument which gives you rain intensity and drop size distribution Of course, it is a point instrument, so it is located over Pune. And the second data set which we have used is Calypso, which is satellite, and we have used the latest standard version 4.02. This is specifically used to identify the aerosol types, that is dust and elevated smoke over Indian region. We have also done some back trajectory analysis and some plots on vertical velocity and specific humidity. So in total, we have actually analyzed 5 different cases, but I'm going to show only 2 cases. The 5 cases span over a time of 2012 to 2019. We are also analyzing 2 more cases for 2020, heavy, specifically the heavy precipitation events. So the first case study is for 21 June 2018. The first plot, which is this, shows the rain intensity and reflectivity with respect to time. So we can see that the reflectivity values reaching at about 50 dBz, and the rain intensity is almost 250 millimeter per hour. The convective transition and stratiform distribution in this particular plot is done according to the Tokai et al. Paper, which was published in 1998. And the convective rain period here lasted for almost 1 hour, from 15:30 local time to 16:30 local time. So this particular figure down shows the drop size distribution. We observe a very broad peak from almost 1 millimeter to 5 millimeter diameter drops. And we have also plotted this drop size distribution for different intensities, such as less than 5 millimeter or 5 to 10 millimeter or greater than 40 millimeter per hour. It is observed that the drops with rain intensity greater than 40 millimeter per hour are very high as compared to lesser rain intensity. The gap is also more. So it is clearly visible that higher drops of for maximum rain intensity or larger were more as compared to the lesser rain intensities. And the total accumulated rainfall for this particular 1 hour of convective activity was for this particular day, period was 73 millimeter. So we also, in order to understand the aerosol types variability and their effect, we plotted dust aerosol optical depth and elevated smoke optical depth. Calypso gives different types of aerosols. In one is dust and one is elevated. So elevated smoke means the smoke which is not present exactly near the surface, but above the boundary layer, or near to the top of the boundary layer and above. So that is what they call it as elevated smoke. So we see that these are the plots for 1 week average prior to the event. So it is clearly seen that there was a lot of dust optical depth, that is more dust aerosols present and less of smoke aerosol present for this particular in this particular 1 week period. The back trajectory analysis also shows the aerosols arriving from a western region, specifically at higher altitudes, about 3 kilometers and so. And so we can clearly see that more dust was arriving at this particular location for during this particular event. The second case study which we have seen is for 25th September 2019. So this plot again shows the rain intensity and reflectivity. The rain intensity was reaching up to about maximum up to about 120 millimeter per hour, and the radar reflectivity was almost similar to that of the previous case study, which is 50 dBz. So the convective rain period here lasted for half an hour only. And if we see in the drop size distribution, it shows a peak at the lower diameter drops up to say 2 millimeter, and then there is a gradual decrease. So there is not a lot of variation between the stratiform and the convective drop size distribution cases. Even if we see the drop size distribution when for different rain intensities, it is seen that though greater than 40 millimeter per hour intensity shows higher number of drops, but the variation in the lower intensities is also not much difference, and the total accumulated rainfall for this particular half hour of convective period was around 34 millimeter. So in order to see the aerosol distribution, we see that there was very less dust present 1 week prior to this, while there was more of elevated smoke aerosols, and the transport was from the Central African continent, that is the biomass burning aerosols which were transported to higher altitudes, as well as from the Indian landmass. There was a continuous source of aerosols over this particular region. So we also saw the vertical velocity during June, that is 2018. There was negative vertical velocity, which indicates upward motion, and the specific humidity at lower altitudes for both these cases was almost same, but at the higher altitudes for 2019, that is the presence of more elevated smoke at higher altitudes, the specific humidity was more as compared to June. So just to summarize, from all the five cases which we have analyzed, we have seen that the dust aerosols caused immigration and high precipitation, while the elevated smoke aerosols caused potential suppression and specifically in the intensity of the rainfall. So we are also dust aerosols actually give more intensity of larger drops and also more number, while the smoke aerosols have less intensity of the larger drops and less number of larger drops also. So we will be also running the WRF-Chem model for these cases and to understand the physical mechanism for these cases. So thank you very much.
Thank you very much. This is quite informative regarding the effect of aerosols on precipitation vertical structure. So any questions from the audience? Any questions from the audience? I think there is no questions. So I have a fundamental question on this.
Yes.
Yeah. So the effect of aerosols on vertical structure of precipitation or the horizontal distribution, can we have a segregation on that thing, like where the impact will be more, whether aerosol can have strong impact on the spatial distribution, or it can have a strong impact on the precipitation vertical structure based on jet profile?
Okay, it will have a strong impact on the spatial distribution.
Okay.
Vertical structure, what will happen is if the aerosols are present on the upper layers, like elevated smoke aerosols, if they are present above the boundary, so they will cause warming and more reduction of the cloud. There will be more cloud liquid water, not clouds present, which will actually rain or precipitate. So that way, vertically it may affect, but it will be on point measurements. But to address this on a larger scale, it will affect the circulation patterns and hence more on a spatial variability.
Okay. Okay. Thank you. So can I proceed to the next presentation? Yeah. So our next presenter is Mercy Varghese, and the topic of presentation is effect of pollution on northeast monsoon clouds. We can see the slides. Okay, over to Mercy Varghese. Thank you.
Hello, am I audible?
Yes, yes.
Is my screen shared also?
Yeah.
Okay, thank you. I am Mercy Varghese. I am from IITM, and I would like to present one of my studies, which is effective pollution on the northeast monsoon clouds. So this study is the study is part of as taken observations on 24/10/2011, that is 24 October 2011, which was taken as part of the GIPEX 2011 observations. So basically, I will be concentrating on the aerosol and cloud measurements done over this region. Here, C and D represent the cloud observations, and you can here see the flight track. That is how it was on that day. Now, on the same day, that is 24 October 2011, was declared as the onset of northeast monsoon by IMD. And from satellite pictures, we can see that there were some deep convection, organized convections happening, which originated over the Bay of Bengal and slowly moved inland with time. And one more thing to be noted is this October-November months is very notorious, being the biomass burning period, especially in Punjab and Haryana and some places in the western Uttar Pradesh. But if you see the MODIS pictures, we do also see like isolated biomass burning patches along the east coast as well during that period. So we had encountered an biomass burning plume during our observations on the location E over here, which is here. And we are trying to see what was the effect of this biomass burning on the deep coastal clouds that formed, which were part of this northeast monsoon. Now, these were the instruments used on board of the aircraft for aerosol as well as cloud measurements. Now coming on to the biomass plume measurements. As we entered the biomass plume measurements, what we basically noticed was an increase in the Aitken mode as well as in the black carbon measurements. And you can also see that there was also an increase in the CCN aerosol measurements. But as we moved more closer to the plume, which can be noticed from the temperature here, increase in temperature, even though the visibility was reduced because of the aerosol pollution emitting the fresh pollution from the biomass plume and the smoke, the BC showed an increase, but you can see that there was no considerable increase seen in the Aitken mode particles, CCN, or the accumulation mode particles, which is mainly because these particles were below 20 nanometer size. And the smallest particle we could measure on board was at 20 nanometer from the DMA. And if you see here, the accumulation mode particles from the PCAS didn't show much of an increase, while we could see an increase in the DMA as well as CCN a little far away from the source. When we looked closely into the size distribution, we also see there is an increase in particle concentration, which was less than 0.3 micrometers inside. So basically, as we all know, the biomass plume, which is always emitting a lot of black carbon as well as very fine mode particles. Now, one more thing to be noticed that this was very close to the cloud base, which was noted that day. Now coming on to the vertical profile of aerosols, here we again see that majority of this is especially the Aitken mode particles from the DMA. Here we see that the majority of the contribution is coming from particles which is less than 0.1 microns. And if you see the vertical profile of CCN and the accumulation mode particles from the PCASP, you see that almost near to 1 kilometer, you see that the CCN particles are dominating the accumulation mode particle concentration, which again suggests that these Aitken mode particles or fine aerosols are also contributing to the CCN measurements. And these CCN measurements were made at 0.4% supersaturation. Now coming on to the cloud-based measurement, there also we see that there is an influence of this increased Aitken mode particles at the cloud base, as you can see from the size distribution over here. So obviously these particles will definitely affect the clouds that are being formed over here. Now coming to see how the CCN measurements, how these particles were affecting the CCN capability of the capability. We did a CCN closure analysis using the K-collar theory. Here you can see the equations used. Since we didn't have any chemistry measurements, we assumed four species. We assumed that the aerosols were purely were internally mixed and were composed of either ammonium sulfate or sea salt or organic, or it was a mixture of inorganic and organic aerosols where we assumed that organic was insoluble. Now, what we can see that even though these measurements were made very near to the ocean, that is very near, it was a coastal aerosol measurement, we do see that the effective hygroscopicity of these particles were very less than that of sea salt, and more or less it was like of ammonium sulfate. As you can see from this point over here, and wherever we had measurements very close to the biomass plume, we see that it behaved, the ambient aerosol was, the effective hygroscopicity of these ambient aerosols were lower than that of ammonium sulfate, and more or less like a mixture of organic and inorganic. So this is because there is a lot of fine mode particles and BC particles present in the atmosphere, which actually, when you see that there is a larger because of this biomass plumes, we are having a larger competition for the available water vapor. Thus, its capability, if you see as a whole, is reduced to become a good CC. Now, if you see to the cloud characteristics. So we had measurements, as I showed earlier, we had two measurements of clouds that was on a location B and C. So one was a growing cloud and another was a mature cloud. So if you see, and these are the vertical profile of the cloud droplet number concentrations from these two clouds taken. So for a cloud pass, to ensure that we are not measuring the edges and we are always inside, we are taking the quantities from inside the cloud, we made a criteria of cloud pass like the FSSP number concentration should be greater than 20, and that greater than 20 should at least last for a minimum of 5 seconds. And the aircraft was flying at a speed of 80 to 90 meter per second. So this ensures that we are inside the cloud and not at the cloud edges or at a dissipating or at any dissipating edges or layer. So what we found that there's a constant increase in the cloud number droplet concentrations at least to 2 kilometers above the cloud base, and this suggests that there might be more that usually we expect the higher number of cloud number concentrations near to the base or a few meters above to the base, but here we see that almost till 2 kilometers above the base we are seeing this increasing number concentration of cloud droplets. This suggests that there is an in-cloud activation which has been going on as and when there are higher supersaturations being available, after which it then reduces. Now, if you see the mean radius, it shows a continuous increase in these, which suggests that even though there is an in-cloud activation going on also, the cloud is also, the droplets are also growing through condensation. Now coming to further seeing into the cloud droplet spectra in detail, we see that at least till 1 kilometer above the cloud base, we see that the dominant mode is the haze particles, which is between 5 to 7 micrometers in size. And even when when we go to higher altitudes, there is still a mode which is distinctively there, which is again suggesting that there is a presence of haze particles in this cloud. So this again suggests that because of this fine particles from this biomass plume, the cloud droplet growth is not, the rate of cloud droplet growth is not as fast, and it is a little bit inhibited. Now coming on to the colder region that is above the freezing level of these clouds, we do find that a few, these are the SIP images, that is the cloud image probe images. And what we see here, the small dot here represent 25 micrometer, that is the resolution of the SIP is 25 micrometer. And we see that small dots which are supercooled liquids. And here we do also see a few raindrops also, suggesting that there is rain forming from above. As you can see that these are actually falling raindrops. And now coming to a little more higher altitude, again we see there is small drops, and very like the ice crystal sort of structures are very little. And in these, even at -3 degrees Celsius. And once we go to higher altitudes, we start to see more ice and gropal structures. The red particles over here has been removed during the processing of the SIP images and are not counted. Now coming to the anvil, again we do see at the anvil top, there is again means you can see that larger ice crystals are formed and they're here. So again, if you see into the ice water content and liquid water content in these clouds, we again notice that there is considerable liquid water content in the cold region, that is above the freezing regions, above the freezing level, and these regions are like nearly -10, -12 degrees Celsius. This suggests that there is an enhanced mixed phase processes happening in these clouds because of the pollution. And the Wegner-Bergeron-Fridolin process, wherein the ice is formed at the expense of supercooled liquids, can be said to be inactive or at a very reduced rate because of this presence of the large number of supercooled liquids and these temperatures. So coming to the conclusions, from this what we understand that because even though it is a coastal region, the ambient coastal aerosol hygroscopicity is less than that of sea salts, but more or less like sulfates. Now, because of a biomass burning plume being there, the effective hygroscopicity of these ambient aerosols are further reduced. Now, because of the large number of fine aerosols present, we do see an increasing CDNC count because even at altitudes like 1 kilometer or 2 kilometer above the cloud base, suggesting that there is a continuous in-cloud activation of these particles as and when higher supersaturations are available. Now, because of the higher number of cloud droplets present, we do see that there are more supercooled liquids at the freezing levels, and there is a dominant process like the WBF process, wherein ice are formed by at the expense of supercooled liquids are inhibited or at a reduced rate. So basically, from all this, what we understand is pollution leads to an enhanced mixed phases in the northeast monsoon clouds. So as a result, what we have, like, it is sort of a deeper as a result of this pollution, there is a deeper invasion of the clouds. So yeah, and with this I come to the end, and I would like to acknowledge MOES and Government of India for funding IITM and KIPEX, the director of IITM, past directors as well as the present directors of the IITM, and the KIPEX team, especially Dr. Tara and Dr. Duncan, for making these observations on the day, and the Tropmet 2020 team for giving me this opportunity. And I would like to thank NASA for providing with the MODIS images, and the NOAA High Split also for the back trajectory analysis. Thank you.
Yeah, thank you very much. So what was the structure of that CCN activation ratio during vertical profiling?
Sorry, activation, I didn't get you, sir. Sorry.
Activation ratio or CCN activation factor. Yeah.
CCN actually, since we had to take the DMA profile, it was at like, what do you say? It had a larger time resolution of 3 minutes almost. So we could, so getting a like activation fraction as such, we haven't gone in that way. Means we haven't found the activation fraction, but only just accounting for the accumulation mode particles, the activation fraction was going above 1. It was like 1.2, 1.3. We haven't counted 8 particles to find the activation fraction actually.
Okay. Sir, your voice is not audible. Yeah.
Now is it audible?
Yeah.
Okay.
Yes.
Merci.
Yes, sir.
You mentioned, so the biomass burning event took place on the day you took the flight observations, or was it before or after or something like before?
Sir, the biomass burning observations were encountered by chance, you can say, while landing towards Vijayawada airport. It was noticed, and those observation was taken during that time.
So the question is how longer? I mean, when did the fires occur and when did you catch it?
We do not know the exact time of the fire occurrence.
See,
So but it was actively burning and giving out a lot of smoke.
Okay, so now that actually connects to your observation on the black carbon, and see, depending on the phase and the time, the type of particles that are emitted by biomass burning, they will vary.
Okay.
So this needs to be kept in mind when you are trying to say this. And the second thing I'm curious to know is that you used the laws to derive which type of particle were present or something. Now, what is the basis? Where did you get this information?
Sorry, I didn't. I'm assuming for the CCN closure you're asking.
Yeah.
So since we didn't have any much of chemistry measurements, I'm assuming these might be the particles present, and trying to see that where the hygroscopicity is lying between, and effective hygroscopicity is lying.
Okay, but please note when you are doing it over the fire, for example, I mean over a fire induced or biomass burning induced. So the other type of particles will be less dominant, no, less prominent.
Yeah, sure, sir. Yeah. I'm showing that, sir, like if you see that slide, it is a vertical profile, and of that, if you see that 4 to 5 points are only said to be near to the biomass burn plume. We
Okay.
have a one which is further away also.
Nice. Okay.
Okay, thank you very much. So we are moving to our next presentation. This will be presented by B.S. Arun. And title of the presentation is Optical Properties and Radiative Effects of Aerosols in the Eastern Himalayas. So, B.S. Can you share the screen?
Hello, sir. Am I audible?
Yeah.
Sir, am I audible?
Yeah,
Yes.
you are audible. Yeah.
I have shared the screen, sir. Is it visible there?
Yeah, you can make it full screen. Yeah.
Yeah.
Okay.
Good morning, all. I am Arun B.S. from SPL VSSC Trivandrum. The title of my presentation is Optical Properties and Radiative Effect of Aerosols in the Eastern Himalayas. While talking about the Himalayas, you are all aware about the severe degradation of the Himalayan glaciers in recent years. There are also rapid changes in the pattern of atmospheric warming over the Himalayan region. Because of these, there are serious climatic concerns in and around the Himalayas, including the effect of monsoon circulations. Hence, accurate characterization and quantification of the radiative impact of aerosols, both directly and through the snow albedo change, is very important. As being surrounded by the anthropogenic source regions of South and East Asia, transport of light-absorbing aerosols and their gradual buildup has become a major climatic concern, as it can warm the atmosphere over the highly reflecting Himalayas, and once it is deposited onto the surface of snow and glaciers, it can reduce the albedo of the surface and could be a probable reason for the retreat of snow and glaciers. In this regard, understanding the optical and chemical properties of aerosols and their interdependencies and connections to radiative imbalance over the vast Himalayas in turn to the global climatic system is of paramount importance. In this aspect, we have started an aerosol observatory at a high altitude remote location in the Eastern Himalayas, Lachung, with the collaboration of MESAC. You can see the laboratory here with our scientific team members. The experiment was conducted during the period of August 2018 to February 2020.
So far, there is no extensive studies of the physico-chemical and optical characteristics of aerosols from the high altitude remote eastern Himalayan location. This region is highly influenced by the outflow of IGP, which is one of the hotspots of South Asia, we know. Earlier in 2019, we have published our result from the Western Himalayan region, Himalaya, which was dominated with the mineral dust aerosols. This study hence aimed to understand the east-west asymmetry, zonal asymmetry in the physico-chemical and optical properties of aerosols. The methodology used here in this study is shown here. This is the extensive set of instruments we have used in the Eastern Himalayan region. It includes the instruments for measuring the optical properties, absorption properties, and chemical composition. In addition to this, the model simulations were used to understand the radiative effect of aerosols in this remote location. Here I am showing the scattering properties of aerosols in this remote region. Left panel shows the variability in aerosol scattering coefficient in 3 distinct particle size regimes, less than 10 micrometer, less than 1 micrometer, and between 1 to 10 micrometer, representing the closed mode aerosols. In all the cases, scattering coefficient shows a significant month-to-month variation with the maximum values during February and minimum during July to September period. Seasonal average values of scattering coefficient indicates that more than 80% of the total scattering is due to the fine mode aerosols. And in addition to this, a clear seasonality is seen in the monthly variation of scattering coefficient due to coarse mode aerosols, having pronounced effect during the winter period and near absent effect during the summer period. The variation of the scattering angstrom exponent is shown in this right panel, which relies upon the predominant aerosol type we know, also support these above observations. The relatively lower values of scattering angstrom exponent during the winter period are found to have a good correlation with the higher values of scattering during the winter period. This suggests that the relative dominance of coarse mode aerosols play a crucial role in enhancing the scattering properties during the winter period at this observational site. Here I am showing the absorption properties of aerosols, which is very important to understand the atmospheric warming. The climatological monthly mean variation is actually shown here. The highest monthly mean values were observed during the March and lowest in August period. Occurrences of the higher values are also seen, though less in percentage. To delineate the distinct source processes in causing this seasonality in absorption, the monthly variation of absorption angstrom exponent is shown here, and its frequency distribution is also shown here. We can see a clear change in this absorption angstrom exponent. The change is prominent from winter to summer and remains nearly consistent in autumn and spring season. Occasionally, higher values of absorption angstrom exponent greater than 1.5 indicates the influence of biomass burning in this location. This figure indicates the monthly variation of aerosol single scattering albedo we have derived using our scattering and absorption measurements. This indicates that the enhanced absorption by fossil fuel-based aerosols in summer, nearly the SSA is going down to 0.6, while those from the biomass burning sources have a lesser impact on absorption during the winter period. Thus, the temporal changes in the SSA during the measurement period indicate the relative change in aerosol size distribution and the chemical composition in this region. This variability actually in the seasonal sources and types of aerosols could be a probable reason for variable heating and cooling rates in the atmosphere. Subsequently, this will affect the stability of the atmosphere. Overall, the very low SSA seen in the observation site is indicating of the strong influence of anthropogenic activities, either local or long-range transported from the distant sources. This comparison of our observed values of SSA with other high-altitude Himalayan sites indicates that this is values are lower compared to the Western Himalayan and the Central Himalayan sites. In order to understand the influence of distinct particle size and chemistry and their relative abundance in determining the seasonal pattern of SSA, we have examined actually the association of SSA with the absorption angstrom exponent and the scattering angstrom exponent. For this, actually, we have partitioned this SAE and AA into distinct domain to delineate the absorbing aerosol species with such as OC representing brown carbon and elemental carbon and mineral dust aerosols. During the study period, actually, most of our measurements fall into the ECOC mixture area. However, measurements during winter fall into the region representing OC and mixture of dust and OC. The mixed aerosol along with the mixture of dust and OC are found to be associated with the higher values of SSA in winter. Similarly, in summer season is also characterized by the presence of OC and mixed aerosols. in addition to the presence of polluted dust. The role of OC and EC mixture is significant in reducing the value to below near to 0.4 during summer period, while the values of SSA remains higher associated with the mixed type of aerosols in this region. During the spring season is mostly dominated by the mixture of OC and EC. But during the autumn season, the presence of mixed type of aerosols in addition to the of EC-OC mixture is seen during this particular time. Since all the combustion processes are producing EC and OC, there is a large overlap between these absorbing particles from the fossil fuel and biomass burning aerosols. Hence, we are not the presence of actually the pure EC and OC are not seen during the present study. The observations till now made so far revealed the clear indication of the very good association of the optical properties with size and chemical composition of aerosols. Higher SSA and alpha absorption in winter is attributed to the significant presence of OC component. During spring, the sulfate enhancement is there that dominates the scattering. Nearly 10 to 20% of the higher OC to EC ratios in winter found to play a major role in dominating the magnitude of SSA, even though sulfate to OC ratios are lower in winter than that in spring. This is favored by actually the relatively higher sulfate concentrations in winter, even though the sulfate concentrations is highest in spring. This figure shows the monthly mean variations of the aerosol direct radiative forcing at the top of the atmosphere and the surface. We have observed a predominant contribution by absorbing aerosols. The surface radiative forcing follows a systematic annual pattern with the highest surface forcing during the months of March and April during the spring season normally, followed by relatively higher values during the September and October. The highest absorption of radiation in the atmosphere during the spring season is nearly 13 watt per meter square. The higher atmospheric forcing during spring and winter could be attributed to the higher amount of EC in this region, thus warming the atmosphere. Even though the OC and sulfate and nitrate aerosols also participate in this atmospheric forcing, the impact of EC is significant in warming the atmosphere, while those of sulfate and nitrate are significant in TOA due to the scattering in nature we know. The estimated heating rate due to atmospheric forcing ranges nearly from 0.19 to 0.4 Kelvin per day, with the highest values during the spring season nearly we can say 0.4 Kelvin per day. The take-home message from the study is that the fine mode aerosols are a predominant contributor in this eastern Himalayan location. The significant presence of anthropogenic aerosols lead to the very low values of SSA in this site, and 10 to 20% of higher OC-EC ratios in winter found a major role in modulating the magnitude of SSA in this region. And highest absorption of radiation in atmosphere during the spring season is also observed from these high altitude remote locations of the Himalayas. Thank you. Thank you, Arun. It's an interesting presentation. So now it is open to the audience for questions.
Dr. Gogoi,
yeah,
there is one question in that Q&A bottom.
Okay.
Next to chat, there are 3 dots.
Yeah, I can see that. Yeah. Is it by Young? Why is SSA decreasing? Increase in absorption during monsoon period.
It's not known whether
Okay.
the question is addressed to
Yeah,
this
yeah.
speaker or other speaker.
Is it for this session or?
This session to have, but whether this speaker or not, that is not sure because they have not addressed it.
Yeah, exactly.
Mukund, how are you?
Hello, sir. I'm fine. Yeah.
I'm somewhere at the top.
Yes, sir. Nice to see you. Yeah. Thank you so much. Yeah. I think this question is for this session, Kundu. Yeah. Okay. Arun, can you reply to this question? Why is SSA decreasing during monsoon period? Is it due to increase in absorption particles or decrease in scattering particles? Sir, actually, it's due to the influence of higher amount of EC we have observed during that period, as well as due to the precipitation, we have seen the more reduction in the scattering properties of aerosols. Both are causing this associated to be lower during this specific period, because it is a region is having very high precipitation during this time. And
Okay,
so the impact of the local elemental carbon emissions as well as the reduction in the scattering aerosols.
Yeah. Okay, thank you. So we'll go to the next presentation. Actually, Kundu, we are slightly behind the time schedule, isn't it?
Yeah, a little behind, but I think we have only, actually there is only one more remaining. S. Karmakar is not there probably. The next presenter, S. Karmakar, is not there, right? Yeah, only so we have only one more.
So now who is presenting? Okay, Devajit Sarkar, is it?
Yeah. Sir, is it audible, sir?
It is audible.
Okay.
So Devajit, you can start. Yeah.
Okay.
Sure.
So I'm Devajit Sarkar. I'm from NRL and IIST. So I'll be presenting that sensitivity of the buoyancy and the vertical velocity to the that intensity of the convection. So I like to thank you that all the co-authors are associated with me in this work. So at first I'll come to the contents. So at first I'll come to the motivation and objectives, then methodology, and then entropy production, and basic concept of that Knudsen layer and Navier-Stokes region, then the sensitivity of the convective intensity to the vertical velocity and buoyancy, then vertical velocity change and the upward mass transfer of the hydrometeors during convection. So at first I'll come to the motivation and objectives parts. So here are some of the pictures I have taken from that Rajiv et al. 2010. So where they compared that emission radar vertical velocity present at the NRL and that model simulated velocity using different microwave schemes. So from that we can see that vertical velocity magnitude in the emission radar is much higher than that whatever model is simulated by using different microphysical schemes. So that means there is some problem in the representation of the vertical velocity in the model. So we have decided how the vertical velocity is changing the intensity of the convection. So this study is associated with that part. Then I will come to the methodology. So methodology for the model simulation, we have taken basic energy budget equation, then the continuity equation for the density of mass air, and as well as for the different hydrometers. Then we have taken that prognostic equation for the mixing ratio and number concentration of the hydrometers. Then we have taken especially the vertical momentum equation. So here we have taken the non-hydrostatic, but here no buoyancy and the liquid water loading term is there. We have added that buoyancy and liquid water term. So buoyancy term is based on the study done by the Wang et al. 2012. We have added here. Then we'll come to that hydrometer species continuity equation, where phi is that mixing ratio or number concentration of the hydrometers, and tau is the stress, and v is the velocity is three-dimensional, and q phi is the source and sink term. So which term we have replaced with that based on the non-equilibrium thermodynamics. So we will discuss that later. And all that prognostic equation solved using central in term, central in space finite defined schemes. Then I will come to the non-equilibrium thermodynamics and entropy production parts. So non-equilibrium thermodynamics, it basically from the name it says that it is not based on the equilibrium thermodynamics. So it basically deals with the transport mechanism inside the cloud microphysical processes and the rate of change of the chemical reaction inside the clouds and how it is changing with times and that concentration. So at first, some of the terms I have taken from this book written by the Bedex et al. So what is the sigma is that entropy, local entropy production, and J is the fluxes, and X is the forces, and Ji is that flux term. We can represent that what is the change of the independent, A is the independent variables, how it changes with time, and X is that forces, how that entropy, total entropy is changing with the independent variables. Then it is the basic equation dW by dt is that for irreversible process as well as for reversible process. So for ideal for ideal equation, that is dw by dt. So what is the work done given by this expression? And if we take the irreversible processes, that means there will be some loss of the work done because of the non-equilibrium processes. So we want to calculate how much loss of the work is done during that any microphysical processes which relate to the entropy change in the irreversible process. So irreversible process entropy, we can calculate that local entropy production over the finite volume, and that the density, as small as the density of the entropy production, can be related to the gradient of the any flux plus the local entropy productions. So what is the, then I'll come to the equilibrium thermodynamics and the non-equilibrium thermodynamics difference. So in equilibrium thermodynamics, we only consider the initial and final states of the phase change. But in case of non-equilibrium thermodynamics, we have to consider not only the initial and final state of the phase change, as well as the in between or the transition state, how much energy is releasing or how much concentration is changing. That thing we have to consider. Then I will come to the Knudsen layer and Navier-Stokes region concept. So Knudsen layer is basically that we used to consider that it is whether it is solid or liquid hydrometeors, and that the outer space, that is vapor phase, that means whatever normal we are taking Navier-Stokes region that we call, and in between what is the transient region. So what is happening that in between transient region, whether some molecule is coming or some molecule is going out from that hydrometeors, that is Knudsen layer. We have to consider that thing. We want to know what is the velocity distribution in the transient, that is the region between Knudsen layer and Navier-Stokes region. So we can be represented by that velocity distribution function, which is given by the Boltzmann's equation. So where positive is that denotes for the emitting molecules and negative denotes for the incident molecules. And for the emitting molecules, the velocity distribution represented by FW plus. So here NW is the density of the molecules, and PW is that W denotes the velocity, and that the actually hydrometeors terms, and P infinity denotes that what is the variables at that vapor space or Navier-Stokes region. And in this for the incident molecule which is coming from the out that Navier-Stokes region to the Knudsen layer, we can be denoted by that AW negative, which is the given expression, or theta is the molecular velocity, and U infinity is the velocity of the molecules at the Navier-Stokes region, and EW is the velocity of the hydrometeors at the Knudsen layer. Then I will come to the some of the simulation, whatever we have simulated, and initial condition we have taken that WRF 2 kilometer run used for the SAR launching at Sriharikota. So for that basic parameterization scheme taken, OIC scheme for boundary layer, and Kenfish scheme for cumulus convection, and this RRTM for relativity transfer model, and Thomson et al. For the microphysics scheme. So it associated with the mixing ratio of the cloud water, ice, snow, grapple, and number concentration of rain, and as well as the number concentration of the ice, as well as the number concentration of the water friendly aerosol or ice friendly aerosol. So from that simulation, the WRM, we can see that there is a heavy rainfall near to the NRL region and surrounding region in 17 to 18, 17, 14 to 17 UTC of 29 June, 2020, and Central India in 1 to 3 UTC of 38 June during 2020, and with maximum intensity of 50 millimeter per hour rainfall. So we have taken only the Gardanki region for our these studies. So we have calculated that the vertical change in the vertical velocity. What is the difference of vertical velocity if we only take Rested equation, and if we take buoyancy plus liquid water loading terms, so we can see the magnitude of that vertical velocity changing significantly. Sometimes we can see that the change is not linear actually. It is changing. Sometimes it is underestimating, or sometimes it is overestimating. So this is the things I have presented till now, and this is the conclusion: is that that present study is revealed that the conductivity intensity or vertical velocity is much more sensitive to the buoyancy and liquid water terms. So further study we are analyzing due to time constant we are not able to present here. So next feature we can present. And acknowledgement. So at first I will like to thank you Director NARL and Director IST for encouragement and for NARL providing that SPC number for the simulation, and we are also grateful to Tropmet 2020 organizer for giving the opportunity to present here. This thank you.
Thank you, Deposit.
Yeah.
So now the session is a presentation. It is open for discussion.
Yes, sir.
Any question from the audience? So can you just tell me what is the primary goal of
yes, sir.
Effective parameterization in climate models? Why do we do that? And
sir, actually most of the model
why it is required to do that?
Actually, most of the model that vertical velocity, they are not able to present properly actually. If we take normal parameterization scheme, because they does not follow that non-equilibrium thermodynamics. Because basically we are taking, if we take the some phase change, there we only consider the initial and final stage. But in between, that transient phase, how much energy is releasing, how much the concentration is changing, we are not at all considering that things. So we want to consider in between stage, how much energy is releasing, how much concentration is changing of any hydrometeors. To represent that properly, we are taking that study actually.
So how do we validate parameterization scheme?
Actually, sir, we will verify with till now is not verified. We will verify with MHD radar vertical velocity.
Okay. Thank you. Thank you. That was it. So
Okay,
any
sir.
other questions from the audience?
Okay, sir. Thank you.
Yeah. So Kundu, now who is the next presenter available now?
Yeah, well, the next to it is not available, so last one probably.
Okay. So it is over, is it? Yeah.
No, one more
Priyanka
is
is
there.
there. Priyanka Srivastava is present. Yeah. Okay. So the last presenter is Priyanka Srivastava, and her title of presentation is Insights from Intensive Long-Term Observations of Carbon Aerosols and Trace Gases at the Central Himalayas. Okay, over to Priyanka.
Okay, I hope I'm audible.
Yeah.
Okay. So, everyone, so my name is Priyanka, and I'll be presenting my work on carbon aerosols and trace gases carried out at the Central Himalayas in the esteemed guidance of my co-authors. So, I want to introduce carbon aerosols to this august audience. Basically, my work actually focuses more briefly on absorbing type BC aerosols and scattering type organic carbon, which have their sources as anthropogenic and natural. And we are concerned about them because they impact our health, cause visibility degradation, affect hydrological patterns, and radiation budget. So this work has been carried out at Aries, which is situated at a mountain at about 1958 meter above mean sea level, and is lying in the close proximity to the populous and polluted IGP region. So we have taken in situ observations using athlometer and OCC analyzers. We have also utilized Picaro for the trace gas measurements. We have supplemented these with satellite measurements such as MODIS and Calypso, and models such as height split and OPAC and SPDAT for trajectory and aerosol radiator forcing. Okay, so this work is some of the observations from 2014 to 2017 for organic carbon and elemental carbon for different seasons. And what can be clearly seen from here is that there is a strong single node diurnal variation. And this lies in complete contrast to the bimodal variations that you observe for the low altitude sites. For example, in Pantnagar, which is just about 30 kilometers from the site. And you can see a bimodal variation here, but at our site, we have a unimodal variation. This is actually attributed to the convective daytime heating and boundary layer dynamics, which bring the pollutants to these high altitudes in the daytime. And this effect is much more prominent in the spring and winter period. Uh, but why we need to consider this, especially because if you translate these afternoon variations and compare this with the forenoon ones, you find that the radiative forcing is especially higher in the afternoon period and goes to about 20 watt meter per square. Then if you come and see the seasonal variations, we see that especially in the spring period, there is a peak in the observations and along with the uh, and this carries out with the mixing layer height and the wind speed, which is higher. So basically, the deeper the boundary layer and the greater the high wind speeds, there will be more polluted transport to your site. But again, there is a twofold decrease in the monsoon period when we have extensive monsoon rainfall, and it accounts for about 68% of the annual. And this is certainly because of the strong wet scavenge. Okay, usually people have been using athlometer measurements to get the black carbon concentration. However, it is to be noted that athlometer gives attenuation. It does not give the black carbon concentration. We obtain the black carbon concentration using the mass absorption cross section, but unfortunately, the mass absorption cross section is considered to be a fixed quantity depending only upon the wavelength in the athlometer. So we have evaluated the values for this mass absorption cross section for the first time in all the spectral ranges at this high altitude site, and we find out that it is about 3 to 5 times lower than the one which is used in athlometer. And there is a significant seasonal and monthly variation in this mass absorption cross section. Why is this important? It is because that if you take this mass absorption cross section, then you find the equivalent black carbon concentration are low by a factor of 2, and which implies that there will be variation of bias in the radiative forcing estimated from this uncorrected black carbon. And we have found out that it can even correspond to a bias in the radiative forcing to about 66%, which is quite high at the top of the atmosphere. But remember, athlometer is a portable instrument, and we can have long-term data with black carbon from athlometer, but this is not feasible with other instrument. So we have corrected this and our black carbon measurements from the athlometer, and we have utilized this, the corrected black carbon values, and found a trend from 2004 to 2020. And you can see that there is a slight decline, a very slight decline in the black carbon concentration of about 17 nanograms per meter cube per year. And if you see this decline at any scale from mean to minima or in various seasons or day or night, there is a slight decline. Okay. Then we have also characterized the various sources that dominate the site using athlometer standard basis model and machine learning algorithm for multiple linear regression, and have translated the fossil fuel and biomass burning from BC to carbon monoxide. And we find that the fossil fuel sources dominate the site in general. However, we also find that the biomass burning components peak during the April and November period. Now, this actually shows that the model had been working pretty well, because this correlates with the peak fire period around the site. We have also used the EC tracer method to quantify the secondary and primary components, and it can be seen that the site is dominated by secondary components almost throughout the period, that is about 62%. Then we also did a case study to identify the contribution of biomass burning, and we find that if you see that this is the green one for the fire counts, during the low fire period here, the concentration weighted trajectories also show that there was a lesser contribution from this region. But if you compare this with the high fire period, we find that the trajectories were much more localized, and but still the emission was coming more from the northern Indian region. So this shows that despite of being at such high levels, we are still prone to transport of pollutants, especially from biomass burning in the northern Indian region. We've also utilized long-term measurements for columnar and vertical distribution of aerosols from, and our results show that when we compare MODIS and Calypso with the MWR measurements for 0.5 degrees around the site, we find that the satellite data matches well with the MWR, especially during the high aerosol load period. And if you see the vertical distribution, we found from the variation of extinction coefficient that there is usual high surface loading of aerosols, but this rises especially in the summer monsoon period. And if you can see here from the from the particle depolarization ratio plots, we find that throughout the period, or mostly the particle depolarization ratio has been less than 0.2, which shows the dominance of fine mode aerosol. So I would like to summarize with this that the study has revealed a strong diurnal variation, unimodal diurnal variation of the pollutants, which induces additional warming, especially in the daytime, and it is unaccounted for if you take offline measurements. And we emphasize here the importance of MAC corrections, which can lead to biased black carbon concentration and radiative forcing impacts. And our results show a slight decline in black carbon concentration at the site with dominance of fossil fuel, uh, except in periods where biomass burning dominates. Further, secondary component has been the dominant factor, and the fine mode aerosols dominate the site. So thank you very much. And I would also, I mean, on behalf of all the authors, acknowledge the ISRO ATCTM and ISRO RP for and DST and ladies for supporting this work, and of course Tropmet for giving me this opportunity to present my work here. Thank you.
Thank you, Priyanka. So I have seen very high PDR during winter at around 8 to 10 kilometer altitude, around 0.3 to 0.4. So is it that?
Yeah, I think I don't think that I mean there's still a preliminary work, so I won't comment. I would say that this is, but still it is about 0.4. So possibly some. I mean, it's not possible that such coarse mode aerosols can reach there. But I think it would be eliminated once we have much more refined. I mean, since this is an average, so there can be a blob, a high value, and which is shown up in the winter period.
I think we can check that data once.
Yes, 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 yes. I know.
So any other questions? So I think, thank you, Priyanka. So there is no questions from the audience. And over to Ramachandran sir. Yeah. So I think this is the end of the presentation. Voice is not audible.
Yeah. Thank you, first the organizers and Dr. Gogoi for co-chairing the session. And I also like to thank all the participants or the presenters who did a very good job and presenting interesting works and keeping the time. And I wish them all the best. And then I hand over the mic to organizers. And thank you, Gogoi, once again.
Yeah, thank you, sir. Thank you, the organizers, as well from my side too. Yeah.
Yeah. Thank you, Professor Ramchandran sir, and also Dr. Mukunda very nicely conducting the session. And also we're on time. We are a little late, but then we have also started a little late. So I think everybody is waiting for lunch. So thank you once again, and all the thank you all the speakers also.
Thank you.
And as I probably my colleague has sent you a small sheet, so I request you to do that, send us that, and also if 4-5 points, because that the Secretary MOES was asking for a recommendation from this symposium. So theme-wise, some recommendation if you feel that can be part of that overall recommendation. So we'll really welcome 3-4 points from Professor Ramchandran sir and also Mukunda.
Okay.
Thank you. Thank you.
Thank you. Thank you.
Okay. Thank you very much.
Thank you.
Thank you, sir.
hear me? Please let me know if you can hear me.
Hello?
Yeah, can you hear me?
Yes, sir.
Okay. Can I try for sharing my screen?
Yeah, just wait, sir. I'll allow you. Now you share, sir.
Thanks.
Yeah, it comes.
Yeah, I just want in the full screen.
Yes.
Can you see the full screen mode?
Yes, sir.
Okay, perfect. Here.
Thank you, sir. Hello, Ashish, sir.
Yes, sir. Hello.
Sir, can you just check, sir? Can you share your presentation?
Oh, okay, sir.
For checking.
Okay.
Yeah. Make full screen, sir. Yeah, it's fine, sir. And also switch on your camera, sir.
Camera. Is it visible?
Yes, sir.
Okay. Thank you.
Thank you, sir. Hello, Jayanti ma'am.
Yes, sir.
Ma'am, can you please share your PowerPoint? Just checking.
Okay. One second. I'm sharing.
Open your PowerPoint firstly, then you share. Ma'am.
Sir, give me some minute. It will take some time.
Okay. Yes, sir. Yes, ma'am. Sorry, I can't hear you.
One second. Screen.
Hello.
Okay.
No, you share your full screen. You share your it's come. It's PDF file. Have you PowerPoint file? Yeah, just open PowerPoint. Just close it. Only share PowerPoint. Only share PowerPoint.
Yes, I have.
Yeah.
Actually, the problem is,
Sorry. I think your network is low. So your
yes, sir. My network is slow,
yes.
and also, sir, I'm hearing echo. Means I'm hearing my voice also.
You hearing your voice?
Yes.
Uh, oh, I don't know. Just check your device, ma'am. Hello. Yeah, just wait. I'll allow. Yes, ma'am.
Yes.
No, no, ma'am. Ma'am, just close it. Firstly, open your PowerPoint. Then only you share your PowerPoint. Only share. Just close the Google Chrome. This one. Just close Google Chrome. Yeah. Please, all windows. So it's equal. Yeah, it's closed. Can you close prompt? Yeah. Yes. Only open PowerPoint. Ma'am, firstly, you listen, ma'am. Firstly, you listen. Ma'am, firstly, you open your PowerPoint. Just, just
Mm-hmm.
minimize the WebEx page. Then you open your PowerPoint. Then
Okay,
maximize
okay.
WebEx page. Then you click share and then, okay.
Okay, okay. Okay.
Hello, Dr. Dibya Jyoti. Hello, Dr. Dibya Jyoti is there?
Sir, he's not right now. He's not here. I'll call
Okay.
him. Just
Okay,
wait.
okay. Because it is time is.
No, sir, he is already logged in, sir. He is already
Okay.
yeah.
panelist.
Okay, already logged in. Yeah,
Yeah,
from his room.
panelist. He is in panelist.
Okay, okay.
Okay, then Dr. Nachiketa.
Nachiketa also here, sir.
Dr. Nachiketa is also here.
Yeah.
Sir, how are you?
Nachiketa.
Yes, sir. How are you?
How are you? Fine, fine. So
Yeah,
it
it's
is,
always pleasure to see you.
it is midnight or?
No, it's actually close to 4 a.m. It's 3:45 now.
Okay, okay. So okay. Thank you for this actually because it is not difficult to visit the.
Thanks for the opportunity, actually.
There is no planning to come to India. Hello.
I'm sorry, you were frozen for a moment.
Yeah, but is there any planning to come to India?
Yes, the plan is always there, but looking for a right opportunity. That's the big thing. And I still remember you told me, in around 2014, you said like, एक बार तो जाओ फिर समझ में आएगा. Yeah.
चल रहा है चल रहा है तो पता नहीं कभी कभी बीच में कहीं हो रहा है चल छोड़ दे चलने दे चल तो रहा है मेरा चल रहा है ओके मेरा तो Dibya Jyoti has come.
Yes, sir. I'm here.
Okay, so can we start now?
Yeah, I think we should start.
Okay, so this is the session on fifth session today. Artificial intelligence, machine learning, and deep learning in weather and climate research and services. And for this, myself and Dr. Dibya Jyoti from NISAC, I am A.K. Sahai from Indian Institute of Tropical Meteorology. So I am chair and Dibya Jyoti is co-chair. So I think Dibya Jyoti, you please take care of if there are any questions after the end of each talk, then we will ask, you have to ask questions to the speaker, okay?
Okay, sir. Sure, sir.
Okay. So then with this, I will invite Dr. Nachiketa Acharya to give the lead talk. Dr. Nachiketa is a lead scientist in IRI, Columbia University. And prior to that, he was in New York City University and IIT Bombay, IIT Bhubaneswar. And he has a vast experience in converting climate outlook or climate forecasts or weather forecast for services. So almost he has 10 to 15 years experience in this, particularly for agriculture and hydrology. So with this, I will invite Nachiketa and he will deliver a talk on the deep learning based multi and this time will be for total time will be 15 minutes. So after 13 minutes, I will give you a warning and you have to finish this. Okay?
Okay, so thank you very much. Just
okay, then start, please.
Let me know if you can see my screen in a full screen mode.
Yeah, we see, full screen first you do, then We can see the screen, but it is not in. Yeah, we can see. Fine.
Okay. Thank you, Dr. Sahai. Always pleasure to have you in the session. And I remember the first paper I read about AI is actually yours, published in 2000 in Climate Dynamics. So it's a very top. So thanks, organizer. Thanks, Dr. Kundu, for making all this hard work. So let's start today's topic, where I'm going to talk about the deep learning based multimodal ensemble. The goal is actually uh, to answer a question like, does deep based multimodal added any value over existing methods? And we know about like multimodal ensemble, which is like a combination of different climate output products uh, to make a decision or make a prediction. Mostly the method available in the literature is linearly is based on the linear regression or kind of little bit of principal component theorem based, but mostly in linear space. Uh, it starts with a simple thing with giving equal weights or averaging, and then giving the weights based on the historical performance of each GCMs. So now I'm going to explore like whether we can use deep learning, because there's a lots of merits, but we also have a lots of demerits if you don't use the deep learning the proper way. So I just started thing, but before I go to the main topic, just want to share my journey with the deep learning, because this is a very fascinating term, and everybody nowadays want to work on that. But it's an interesting thing, but it's also needs lots of understanding before using this thing. So for me, whenever I listen this machine learning or deep learning back in 2000, maybe around 8 or 9, it was very fascinating, and something coming to my mind is like either the movie Terminator or the human robot Sophia. But slowly, when I start reading those literature, it's for me, it's all about black box. I don't even understand how these things work, because I thought like in my background is statistics and mathematics, I can understand those things. It's not so easy. So for me, it's all about black box that time. Then I start talking with different computer scientists, civil engineers, and reading more of the paper, and got different perspective for everyone. It's remind me a story, like when like, there's a funny story like a 7 8 scientist, and everybody eyes they close their eyes and they try to understand what is this animal, which is actually an elephant, and then they give their assumption based on wherever they touch. And same thing happened with me wherever I talk with different scientists, whether in India or outside. I got different perspective of machine learning. Mostly it's nonlinear modeling, or it's genetic algorithm, or it's logistic regression. So it was not so much clear to me what is the root of all the system, or what is the actually the whole system about. Then after some struggle and reading different papers, what I understand about deep learning is actually basically a universe of artificial intelligence, and anything like machine can solve like a human is artificial intelligence, but there is some subsets. So the first subset is machine learning, where we actually use different algorithm to allow computers to learn from the examples. Within the machine learning, there is another subset called artificial neural network, which is actually inspired by the brain mechanism. Within the artificial network, the sophisticated is deep learning, where we use, more complicated mechanism of the brain. So that's like all about the deep learning. And as it's all about the learning, it's also important to know like how to use the learning system in the computer. And basically, it's a two-way. You know, imagining that you are going to school and there's a teacher and teaching you what to do. And the unsupervised is like the way I learn actually, because I kind of, learn reading different papers and other things, kind of learning by myself. So it's kind of unsupervised. Another example, like in supervised, like for example, in this cartoon picture, like you make a notation that these fruits are actually apples, and then you feed the system, and after a certain time, the brain can actually, or the artificial brain can actually predict that this is an apple. So it can be used as a classification, it can be used as a regression. But for the unsupervised, it's mostly cluster analysis, like you give the data and the system start understanding from the data, and then it's actually classify or cluster the data in a different classification. But the important thing, see, like regression is also supervised learning method. So next time when I do the simple regression, you're actually doing the machine learning. So it's like it start with a very fascinating thing, but it's ended with a regression kind of linear regression thing, and that's what I'm thinking about. Like, okay, so we can use this whole system for some kind of regression because we start with like, can we make a different kind of regression for the multimodal system? And that's what like I know I was down. Okay, so we can do it. So basically using the supervised, but as I'm talking about deep learning, and deep learning is a subset of neural networks. So we almost like everybody in this panel, we know about neural network is actually inspired by the real mechanism of the brain, but it's actually very interesting. It's actually established this fact in 1943. It's a very old one. It's not like something happened after 2000, but the interesting thing is like it's became more popular recent years because we have lots of data to play with. So before that, the concept was there, but nobody actually explored more due to the lack of the data. So, so it's actually a mathematical interpretation of how the brain works, how the system of the information within our brain actually go through the different dendrites. Basically, it's having different information and then it's processed in the cell body and then goes as output in an axon. And if we just make a little bit of more complicated, it's look like this. So the red dots are inputs, and then there's a hidden layer, which is like a cell body, and then the output. So these are simple neural network system, but you can make more complex if you add more hidden layers, more hidden nodes, and then it makes deep learning. So on that, I just also a little more understanding about like because we have to understand the mathematics behind like because we have lots of software and the data can feed those software and at the end we should have something, but unless we understand how it works we cannot use in a proper way. So again I'm kind of understanding this thing at a base of the linearization. So for example, these are your predictors or inputs x1 to xm, and then there's a different weights, and then there is a like a firing condition, like some condition like if this like if the combination of these weights and inputs greater than some value, then we can actually process the signal. And to process the signal we need a different type of function they call activation function. So it can be a linear, it can be a sigmoid, it can be a tan hyperbolic, different kind of on the program. So on that, the most popular system, basically in the climate science, is actually single hidden layer feed forward because we understand more because it's a single hidden layer. There's no more complication, and the way it works is actually going a different way. So again, the inputs, and then we make some kind of process in the hidden layers, and then found the output, and then we compare the output. If we are not satisfied, we again bring back this system we call back propagation. So that's the way it works. So in that sense, we can understand from the black box, we can get some light that is something going on in an iteration way using some kind of regression fundamental, and it gets some idea. And people are using a lot of this thing, and they also use a multiple hidden layers. But there is a strong limitation of this kind of methods. Basically, I'm going to use this system for multi-model where we have a very less number of data set because those climate models have only 30 years or 25 years hindcut. So we can't use very sophisticated method if you don't understand and if you have a less data set. The main limitation is actually it's highly based on the tuning of the parameters. So basically you have to make this thing and tune and again, so we can't use it like a operational mode. Second, it took a long computational time. It also have a over-tuning problem. So that's why like people mostly criticize using the neural network in our field because they said, oh, it's all about over-tuning. The result is super because it's actually over-tuned. And it's actually true because if you have a less number of data set, then it's this whole limitation can become there. So on that, we kind of searching for a system where it's most simple, but we can also have some kind of authority to change the system. And then we found a very interesting system called extreme learning machine. So it's very interesting, like from machine learning to learning machine. So it was invented in 2008 by Professor Huang from Singapore, Huang Technology University, and it was like a very brand new that time when I started working, and people mostly criticized this. But like slowly in 2020, there is a big community on ELM, and people are using all over in the world, and different things. So the interesting thing is like the weights in the system is chosen random, and then it start the system, which is actually make it a very simple and like choosing the weights in a layers in a random, make it a very kind of a linear system, and then instead of using a different a complicated computer science based algorithm to estimate the parameter, they actually use a very simple way. It's called a generalized inverse or G inverse. Like it is a very commonly used system in the mathematics. So that makes everything is very simple. So it's look like this. You know, it's look like very non-linear in the beginning in the hidden layer, but at the end, it's actually a linear system. Basically, like imagining solving a generalized linear model, a GLM kind of things, but using the analogy of the brain and using a very simple but sophisticated system. So I like this system a lot, and it's actually make this whole understanding of the black box like a white box, because we can have the control, like, you know, we can actually change everything based on the understanding. And the super important thing is it's actually 1,000 times faster than any kind of traditional neural network, which actually helps us a lot because we don't have a big computer to run those kind of things forever, especially for the multimodal. And I'm working in mostly in the operational focus system, so we can't wait like 7 or 8 hours to run the operational focus. So that's what like this system is very promising to me at that time. So based on that, I did lots of exercise. So one of thing I just want to share today is actually the prediction of the winter Indian monsoon or northeastern monsoon. As you know, this monsoon has a huge impact in the southern part of India. It's also contribute more than 50% of the annual rainfall. And this is a plot where, like, compared to all India, Peninsula, and Tamil Nadu, we can see there is a, you know, huge important for this system. In fact, like we are actually within this post-monsoon season right now. So, and also like this, the variability of this monsoon is not simple. It's as complex as the summer monsoon. So it's a problem to work. And the aim is actually making the MME using, you know, this deep learning. So to start with, I just plot some models which is based on North American multimodal ensemble. So the navy blue or the blue one is actually the IMD observation for that region. And I'm sorry. Okay, so this is the state about the model. So from that, and we know, like, you know, the problem with the model because of the poor teleconnection pattern. For that, I started making this ELM system. So how it works? So we use the input as a 7 GCM of like output from the GCM, and then we scale the neurons, and then use some kind of a sigmoid activation function, and then we train and test. And that's the most important things here because we don't have a much data. So we use the cross validation method for train and test, and we ended up with this system called 7, 25, and 1. And this is the scale. And if you compare the observation and the E, which is ensemble mean, and MLR, which is simple multiple linear regression, compared to ALM, it's a huge because it's actually bringing that variability from each model, which is we lose because we just make a simple average. And if you plot the box plot, you can also see that the interquartile range is as similar as the observation. We also use a little bit of more skill evolution, like different kind of, you know, multiple group bias, correlation, remote index. In every case, is actually very promising. It's also giving us a very good prediction of yield. I also calculate the deficit and excess year based on this data. And if you compare the simple method and the ELM, is ELM capturing this discrimination between the below and above years. So on that, I just want to conclude that this system, which is more on the white box, is actually capturing the variability of the system, which is we miss all the time when you make the MME. And we kind of blame the GCM output, but it's actually not, because we are actually underestimate the GCM output. So on that, I said, but we also need lots of data, like to have this thing. On that, I just want to one note that neural network is awesome things if you use properly. Like this is a very new one things. One of my friend is working in the system that they actually capture this thing, to make the COVID thing. But at the same time, if you use improper way, then we should have this kind of problem where the camera is actually chasing to the bald head referee than the ball. So important thing is like we should use this whole system in a proper way and in proper understanding. Thank you.
Thank you, Nachiketa. So, Dr. Dibyajyoti, there are some questions.
No, sir, it is a very good work, and definitely he is going in the right direction. And I think there is AI has deep learning has a lot of scope in weather forecasting. We are also trying. Thank you. It is a nice presentation.
Thanks. I'm sorry I was very fast.
I have one question to you. Actually, when I was doing long back, 20 years back, there was some Kesar formula or something that you should have 30 times more data set compared to your free parameters. So here the free parameters are number of weights, means number of hidden layers, and there are biases and weights both, so double of that. So in deep learning, there are many layers, hidden layers, and this. So how this problem is, as you told, overfitting and this, how this problem is being tackled? Because earlier statistically, it was told that at least 30 times more data is required than the free parameters. So is there any thought on this?
Yes, sir. Actually, like again, like the important is systems like where you are using. For example, this kind of system where we have like 30 years of data set, like we don't have much data set. That time, that's what I always go for a single layer, very small number of nodes, and having a one stopping criteria instead of three or four stopping criteria. So you should customize the whole system in such a way it looks like a linear, but not. In the same time, we can use a less number of data. And that's what I like this network a lot, the extreme learning machine. Because if you use a simple SLFN and others, it has some same problem like you explained in the overtuning. So I can say like for this system, we should go for this kind of system because we can take care of that.
Okay, thank you, Nachiketa, for nice talk. Thank you. So now we have 10 talks in this session, and I will give 8 minutes to all the participants and the presenters. So after 7 minutes, I will give you warning, and within 1 minute you have to finish once I give the warning. So the first presenter is Mr. or Dr. Ashish Shakya. So he will be giving a talk on integration of machine learning technique in short-term precipitation forecasting using radar data. So whether Ashish is there?
Yes, sir. I'm here.
Yeah, please start.
Okay. Good afternoon, everyone. My name is Ashish Sakya, and I am here to give a short presentation on our paper entitled Integration of Machine Learning Technique in Rainfall Forecasting Using Radar Data. The authors are myself, Mr. Avinash Chavan, and Dr. Divya Jyoti Sutia. Moving on to abstract. As rainfall prediction is one of the most important things to be achieved accurately, our main aim here is to build a model using artificial intelligence technology for prediction of rainfall solely using radar image data. For this, long short-term memory, also known as LSTM, with convolutionary structure has been used to process the radar images. The general speed and direction of movement of the clouds has been estimated accurately. The introduction. To build a working prediction model which processes radar image data is very challenging due to the continuous change in atmosphere. The main drawbacks with the other techniques such as ARIMA model, support vector machines, also known as SVM, backpropagation algorithm, and fuzzy logic are the data used with them are statistical and numerical data, which leads to inaccurate predictions, and we have to use our assumptions in most of the cases. So the weather data that we are using in this project has various advantages over traditional numerical data, such as high quality of data, reliable weather forecast, more accurate results, and many more. As data used here are collected in a time series manner, machine learning model based on LSTM is being used, as LSTM contains memory cells to store the previously calculated information and uses that information with current information to produce an output. Although LSTM layer has proven powerful for handling temporal correlations, it contains redundancy for spatial data such as images. So as we are dealing with images, radar images, instead of internal matrix multiplication, which are generally there in LSTM, is replaced with convolutionary structures from input to state and state to state transactions. The main objective of our project is to build a model using artificial intelligence methodologies which can accept radar image data as an input and process it to produce a predicted output as a radar map in 15 to 20 minutes into the future. The data sets that has been used is data is being used for this project is the data used in the Conference on Information and Knowledge Management, also known as CIKM, and is taken from Alibaba Cloud and downloaded. It was downloaded in a binary format. There were 3 text files, train.txt, which contains 1,000 images, radar images, and is 17.1 GB long. And there were other 2 text files containing 2,000 radar images. Each text file contains real radar map information and the rainfall amount of different sites collected by meteorological observatory centers. Data sets which were radar radar map information covers several dimensions as follows. At the center of every single map has one target site. At different period of time, the maps were measured data sets, that is 15 period of time between fixed point in every 6 minutes of an intervening time and 4 different heights in 1 kilometer of an intervening time from 0.5 kilometer to 3.5 kilometer. Area of 101 kilometer into 101 kilometer is covered by every radar map around the site. So for the previous problems, the solution strategy where few of the images are hidden, non-hidden images are studied by the model and trained on them. The model gives the predicted image as an output, which is then compared with the ground truth. And we achieved that by setting up a network structure and piling up numerous convolutionary layers. An end-to-end trainable model for short-term prediction of rainfall is built. The diagram states that figure 1 diagram states that the radar data was first, as it was in a binary format, so it had to be converted and stored in some other file format for easier to easily manipulate and use store the data. Then the data was read and loaded from the converted file format, that was .h5 file. The model sequential model with LSTM convolutionary structure as layers. Activation functions that we used were ReLU and linear. Loss function model had 40 filters, kernel size of 3 into 3, and input shape of the image was 101 into 101. After that, the model was trained, then trained on 2,000 samples and was tested on 120 samples, and the predicted result was there, and at last the visualization of the images were done. So the integrated architecture that we used was in figure number 2. It is a 1-layer architecture. The radar images passes here. The radar images passes through convolutionary layer, where important features are extracted by various filters, and the output that is achieved are connected to a fully connected dense network. After that, each of the layers was stacked on top of one another and formed two networks, first network and
Please
second
finish
network.
in 1 minute, please.
Then the structure consists of two networks. Both structures are created by stacking multiple layers together on top of one another. The last state of the first network are copied to become second network's primary states and outputs. The result, although the results came out to be blurry, but when it was compared with the ground truth, the assumptions, the predicted output were accurate, as you can see in figure 4 and 5. So to conclude this project, radar data can be used for short-term prediction of rainfall, artificial intelligence methodology, and the limitations was radar data are very complicated to be operated upon and require updating on the current model if another set and different format of radar data is to be used for prediction. And for the future scope, the extension of this project, we will be using Indian radar data as data set. Thank you. Sorry, sir?
Dr. Dibyajyoti, I'm asking Dr. Dibyajyoti, is there any question?
Yes, sir. Yes, sir.
Yeah.
Yeah, Ashish.
Yes, sir.
How are you? Fine.
Yes, sir. I'm fine, sir.
Yeah. So now that you have improved your model, that.
Sir, a bit is improved than it was when it was worked upon. Now I have to create a model for a new model has to be created for accepting different data sets.
You can try for that now, that transfer learning one.
Oh, okay, sir.
So that is a new one. That is it is giving very good results.
Yes,
For
sir.
all case of data, particularly any benchmark data, you can try.
Okay, sir.
You can take Indian radar data and work for that. Why you are taking that stack data and other things? So Ashish, what is ReLU function?
ReLU function is rectified linear unit. Common CNN functions used, and the negative. Sorry, sir. Sir, I'm not able to hear you.
ReLU function, how it is defined? Okay.
Sir, ReLU function neglects the negative data and just puts instead of negative data, it puts 0 in place of that. So,
but that depends on your data. Huh? How are you inputting your data? If you are putting in a standardized data, there will be negative, positive, both. So that depends which problem. Okay, thank you. So now I will invite Mr. KV, Dr. KV Subramaniam.
Yes, sir.
So, yeah, please give presentation. So you will be also having time for 8 minutes. So after 7 minutes, I will say you and you have to.
Yes, sir. Yeah, good afternoon, sir. Thank you, Professor Saha, sir, for giving this opportunity. Myself, I am Subramaniam. Title of the today's talk I'm going to tell is Forecasting of Time Series of Geophysical Parameters using GPR and LSTM models. Actually, this work is done by, intercollaborative within the ISRO. As a part of DTDA, ISRO headquarters initiated this one just 1 year back. This is what we have carried out. And outline of our presentation, I will be just giving a brief introduction and what is the data source used for the present study and what are the models along with the validation. I will be concluding with the summary and feature scopes. And when you say, this AI as well as machine learning models, we immediately remember the numerical weather predictions, which are called as a convection models, are capable of solving the complex systems of nonlinear equations, which can, govern the behavior of the atmosphere as well as other sophisticated computational facility. But given the existence of a large volume of data, these ML or AI algorithm models can learn the behavior of the state of the atmosphere and could able to predict the very near forecasting compared to the NWP, where NWP model takes 3 to 6 hours spin up time for prediction, whereas AI models, the spin up time is almost negligible. But at the end, if you can try to blend with these forecasting of prediction of both conventional model as well as AI based models, which can help in improving the better forecasting accuracy for our day-to-day regular purpose. So the main object is to build a model for the forecasting of time series of geophysical parameters using GPair as well as LSTM over a given region. In the project, what we have taken is the shore region is the given regions. And any state of the atmosphere can be defined by the primary 5 important geophysical parameters. Those are atmosphere pressures, temperature, rainfall, humidity, wind speed. So there are many various other parameters, but the response of all these state of the parameters can be defined by these 5 geophysical parameters. So in this study, we have used the primarily these 5 important parameters for building the AI over the shore regions. And what we have used the data is 16 years of the 1994 to 2009 hourly data measured from 100-meter tower for wind speed and the surface observations of temperature, pressure, humidity and rainfall had been taken for the present study. So a total of 131,400 hourly measurements were collected. And this table gives what is the dynamic range of all these values along with the standard deviations. And so obviously the data is formatted with the time tagger, and also we have identified the bad data points and eliminated from the data analysis before training the model. So the missing data are filled with the 3-hour interpolation data using linear interpolations, and the data are divided into 80% as well as 20% of the validation. So as you all know that there have been various machine learning algorithms, but we have used mainly 2. One is Gaussian process regression, which is a univariate, as well as LSTM, long short-term memory model, which is a multivariate model. So comes to the GPR univariate model. So this figure shows the heavy rainy days, which includes moderate to heavy rainy days as per our IMD classifications. Blue color gives the train data, whereas green color shows the actual observed data, and red color gives the predicted data. So from this picture, we can say that overall the predictions are good and able to reproduce the variability of the rainfall. And also interestingly, one could see that it could able to capture the peak years of the heavy rainfall days. And again, this is for 2006. This figure shows the March to April of wind speed time series, and the right panel shows for pressure, wind speed, pressure and temperatures. See, why I am showing this March to April is this is a normal conditions where the univariate model is able to capture in all the variation, because which is having a periodicity in the time series, so it could able to capture. And this is same for May to June, which is the onset of monsoon. And whereas for pressure and temperature, it could able to pick up, but whereas wind speed, again, there is a slight disturbance is there because this is a monsoon onset time. And when it comes to the disturbing period, that is during the cyclonic period, October to November period, where the 2006 Ogni cyclone is there, as usual, pressure and temperatures, where they have the periodicities, it could able to pick up, but the wind speed, GPR could fail to predict the during wind speed conditions in the disturbed period. This is because basically, the GPR is a single variate, which we are not taking into the other parameters. But in the real case, all the geophysical parameters are interdependent among the other. So when we are trying to predicting, we should take into these models. So we have gone for the LSTMs. So before I go into the LSTM, again the GPR predictive model for zonal wind over the Tumba, where we have the very long time series of the radius wind data is available. So the top panel shows the zonal wind normalized for predictions using GPR.
whereas zonal wind observed in the below bottom panel shows the observed one, this monthly. So we can see that very nicely it could able to capture, sir, because this is very the zonal wind speed having a annual oscillations, as well as at 20 kilometers also we can able to see that very nicely the oscillations it could able to pick at. The time series plot it shows that very nice it could able to predict. So for comes to the single parameter, so this kind of univariate model, it can straight away we can able to use it when we want the things. But when it comes to the multivariate model, yes, this is a multivariate. What we have taken is the data formatted, data cleansing, and we have used the 60 neurons, and the output layer is 12 hours prediction, 24 hours, 36, 48 hours. We have used the TAN-H as well as Adam optimizers, and loss function, what we have used the mean absolute error. And again we have predicted the test data and also calculated the matrix like mean squared error as well as R squared values. So that I will be coming back. So apart this LSTM, we have used the sliding window techniques. This sliding window technique approach transforms the problem of time series into a supervised learning problem, which enables the prediction of future weather parameters. This training data is sliced to batch sizes of 256 count. So each buffer is scheduled to 5%, so that in order to avoid the bias learnings. So that's the way. So the number of batches will be varying as a future predictions. For 12 hours, the predictions will be 72 hours as well as 12 hours. 48 hours training data, we have taken the past data 72 hours and 48 hours predictions like that. So this gives the result of the LSTM temperatures, 12 hours prediction, 24 hours, 48 hours. You can see that for 12 hours, very nicely it could able to the captures. When it goes, the time is increasing, forecasting period is increasing. It is slightly deviating with the observed one as expected. And this is also shows the pressure for 12 hours, 24 hours, 48 hours. And this is also relative humidity also. And the wind speed also you can see that. But again, what we have tried is here, this shows the wind speed maximum. Since we have the
1 minute.
Yes, sir, thank you. This wind speed maximum we have calculated, and this LSTM model also could able to capture this one. As I said, for very short time, these AI based models could be able to predict better. When it goes to the longer period, it is deviating from the actual observations. And this is the rainfall, but this LSTM could not able to predict as good as compared to the which have the very nice periodicities. Whereas rainfall it is not able to pick up, but though it could able to capture the peak time of rain rate, as we can see in this figure. So further, this is the scatter plot of all the things. As I see, we can see that for 12 hours correlation is very good. When it going, the correlation becomes worse. And apart from this, after predicting the LSTM data, we have try to compare with the other independent data set like a IMDA, that is NCMW free analysis data for wind speed. We can see that very nicely it could able to predict the in the wind speed case. And this is a validation. You can see that apart from the LSTM, we have also used the simple recurrent neural network as well as gated recurrent unit also. These are the validation matrix, and this is a summary. So we have used an attempt is try to make the ML algorithms for weather prediction over the shore, especially. And their proposed LSTM is kind of base model, can be employed for predicting the weather parameters, but before implementing, it has to be rigorously validated properly before indicating to the operational whatever. And the future projection is yes, the rainfall is yet to be improved more. So different configurations of LSTMs has to be investigated for better hourly rainfall. Even hybrid models also we have to take it. And thank you, sir.
Okay, thank you. Thank you very much. So, Dr. Divyajyoti, there are any questions from the audience in chat box? Hello? Hello? Dr. Divyajyoti?
Yes, sir. Yes, sir. I have checked the chat box.
Yeah.
There's some question to Dr. Sarkar, not here actually. Anyway, sir, recently I have seen this presentation during our review meet of ISRO.
Okay,
anyway,
fine.
Nice work, sir. Yeah.
Okay, very good. So, Mr. Dr. Subramaniam, do you suggest multivariate LSTM or univariate?
No, sir. Multivariate is the one we have to go, sir.
Okay.
I prefer multivariate, sir, because what I try to show it is, in order to get the feeling of a multivariate model, so we have explained the univariate, so that, for one variable, that is only time series is going into the input, not all the parameters. Sir. So that is not the one we should go, as per I consult, sir.
Okay, thank you.
Thank you, sir.
So now we have
yes, sir.
And yeah, you please share your and you will be having 8 minutes. After 7 minutes, I will tell you to stop. So 1 minute you have to wrap up. Okay. Thank you. Please start.
Thank you. Good afternoon to all dignitaries. Forecasting the tropical artificial neural network over the North Indian Ocean. So we know that the tropical cyclone is the most vulnerable phenomenon over the North Indian Ocean that occur during post-monsoon and pre-monsoon season. And it is very important to understand its track and intensity because it can cause a huge destruction. So here, in my work, I have done some kind of small effort. It is a small effort to find out whether we can predict the category of the tropical cyclone with a suitable lead time. For that, actually, I have taken the wind speed and the central pressure drop. Although in Indian Oceans, North Indian Ocean, wind speed are considered to be a prime factor to define the intensity of the tropical cyclone, but I am here taken the wind speed and central pressure over the North Indian Ocean. And hence, I have framed my objective one is the assessment of the prediction of category of the tropical cyclone using wind speed and the central pressure, which parameter is good. And the second one is the predict accurately the highest, that is maximum stage that is identified by the wind speed and the central pressure drop over the North Indian Ocean using artificial neural network. For that particular thing, actually, I have collected the data from the Indian Meteorological Department. Data, which comprises the 3-hourly data, and the data period is for 1990 to 2019, that is almost 30 years. For these 30 years, I have taken the data over the two ocean basins, that is Bay of Bengal and Arabian Sea. Over Bay of Bengal, I have collected 57 cyclonic systems. Among the 57 cyclonic systems, there are 7 deep depression, 18 cyclonic storm, 9 severe cyclonic storm, 12 very severe cyclonic storm, and 11 extreme severe cyclonic storm. And over Arabian Sea, there are 33 cyclonic systems. Among them, 12 are deep depression, 8 are cyclonic system, 5 are severe cyclonic system, 3 very severe cyclonic system, and 5 are the extreme severe cyclonic system. In this study, actually, I have removed the super cyclone because there are very less amount of sample to analyze the data using the artificial neural network. Another meteorological data I have collected from the NCEP-ENCA reanalysis data. Sea surface temperature data has been collected from the NOAA high resolution blended analysis of the daily sea surface temperature. And to calculate the low level vorticity, I have used here the cross calibrated multi platform ocean wind vector data that is provided 6-hourly data at 25 kilometers per resolution. So in this present study, I have considered the variables which are important for the formation as well as that are important for their intensification. So first one is for the low level vorticity, that is calculated from the cross calibrated ocean vector wind at 10 meter. Inverse of the wind shear. Wind shear is calculated between 850 and 200 hectopascal. Equivalent potential temperature difference, that is calculated between the surface and 500 hectopascal. Mid-tropospheric humidity has been taken by taking averaging between 500 and 600 hectopascal. Along with that, I have also collected the vertical velocity at the 3 standard pressure level. Now, to collect the data, actually, I have mostly focused on the eye area. Now, for that, actually, I have considered a technique that I have collected the data by averaging like 2 degree within the 2 degree radius. For that, actually, I have taken a swath with a radius of 2 degree, that is around the observed point. All the grid points that come under the within this 2 degree radius has been averaged to yield a single value for every variables considered in this present study. Now, the implementation actually for every cyclonic system has been divided into two sections. One is the sections when the cyclonic system attain its mature stage. The mature stage, that means the maximum wind speed or maximum central pressure drop. That point is identified as a 0 hour data. And after collecting the 0 hour data, we have divided the previous section of the tropical cyclone into the 6 hourly with the 6 hourly lead time, starting from 6 hour to up to the 90 hour lead time, and then we apply the principal component analysis on the 0 hour data, and from that principal component analysis, significant parameter has been extracted, and those significant parameter has been used to prepare a matrix for input for artificial neural network. Here, the centralization has been used to standardize the data, and the training purpose over the view, I have taken the 48 cyclonic system. Over the frequency, I have taken 26 cyclonic system. And artificial neural networks, among the along in the artificial neural network, actually, I have framed on radial basis function and also the general regression linear neural network. That there are different types of neural network has been run for every lead hours, and for every lead hours there are 10 neural network has been run, and among the 10 neural network, one best neural network has been chosen for every lead time, and then this single model for particular for every hour has been evaluated using the error analysis, and then best model that with the best hour has been validated with the has been validated for the rest of the data. From the principal component analysis, actually, I have done the principal component analysis. From the principal component analysis, it is observed that over the Bay of Bengal, mid-tropospheric relative humidity, low level vorticity, vertical velocity at three different standard level, that is 850 hectopascal, 500 hectopascal, and 200 hectopascals, are found to be insignificant parameters.
Please
Whereas
finish
over
in 1 minute.
RBNC,
Jayanti, finish in 1 minute, please.
okay. As a over Arabian Sea, there are MR, mid-tropospheric humidity, sea surface temperature, vertical velocity 200 at 200 hectopascal, equivalent potential temperature difference, and inverse of the wind shear are the five major that are found significant, and that those are actually used for the input in the artificial neural network. Here we have the base neural network for pressure drop and maximum wind speed. So we have run each model for each hour over Bay of Bengal, and in this evaluated using the error matrix, mean, absolute error, potential error, and root mean squared error. From that, actually, we see that over Bay of Bengal, the using the pressure drop, we get a minimum error for the 6 hour lead time, whereas for wind speed, we get a minimum error for the 60-hour lead time. Over Arabian Sea, for the pressure drop, minimum error has been observed at 36-hour lead time, whereas for wind speed, we observe minimum error 48 hour for the 48-hour lead time. And here we compare the observed for the base hour, whatever base hour we have from the error analysis. We compare the observed and predicted data for the best hour, and here we observe that for Bay of Bengal, there is a little bit overestimation for the lower value and a little bit underestimation for the higher value, whereas for over Arabian Sea, it was quite predicted well. And validation also shows a little bit, that is basically as the validation samples are less, but it was the validation samples are used for up to 2019, and it is observed that it is quite also supported our analysis, but still there is a overestimation of the lower value and underestimation of the higher value, and Arabian Sea also shows a better prediction than over
drop is have RMSE of around 1.5 hectopascal at 0.6 time, whereas wind speed at have 8 of 4.62 knot at 60 hour time. Over ambient situation, drops are better predicted for 36 hourly time. Although the error is a little bit higher than the Bay of Bengal 2.2 hectopascal. Maximum wind speed we can see here that it is 8.45 knot at for 48 hour lead time. And structural purpose, you can see that over the Bay of Bengal we have we require one node for wind speed forecasting, whereas for pressure drop we need two nodes for pressure forecasting. Whereas for RTC only we require one node for both. So we see here that wind speed is better predictor for forecasting target, that is the category purpose, and also forecasting is a little bit better than the Bay of Bengal regarding the observation where we compare the observation and the prediction value. Thank you, sir.
Thank you very much. Are there any questions, Dibyajyoti, in chat?
Yeah. I have one question.
Okay, okay, please.
Like Jayanti, now you are mentioning that in your implementation, that
yes,
what is the significant parameters and how you are measuring the significance?
I have used the principal component analysis, and using the principal component analysis, I have extracted the whatever parameters I have found significant using the principal component analysis. I have taken for that only for artificial neural network.
Okay, one more question. That you are mentioning that you are getting some underestimation and overestimation in your prediction.
Yes, sir.
What
Yes,
could be
sir.
the reason?
So that might be either because I have taken the data, first of all, from deep depression to the extreme severe cyclone. There is a large data variability. So that might be the reason. So for that, actually, now actually I'm trying with other source of data so that we can minimize this thing actually.
You also try to check your model whether it is generalized properly or not. It is just
Sorry, sir.
you're
Hello?
getting you see that whether your model is generalized properly or not with all kind of data. Anyway, thank you.
That also we need to check, sir.
Yeah. Thank you.
Okay, Jayanti, very good presentation. Actually, in general, also models are having good skill in Arabian Sea compared to Bay of Bengal. Not only for cyclone, but for other things also. So your results are very much consistent, even it is with neural network. Thank you very much
Thank
for
you, sir.
this.
Thank you, sir.
So now I will invite Dr. Ajay Upendra for his presentation. Is he there? Present? Ajay?
Yes, sir.
Yeah. Please you start. So after 7 minutes, I will tell you to finish in 1 minute. Okay?
Yes, sir.
Yeah. Share your slides.
Hello, is it visible now?
Your voice is very low.
The slide is visible?
Slide is visible.
Okay, sir, I'm starting now. Good afternoon, everyone. I am Ajay Savdekar from the Walchand Institute of Technology. My presentation is on the meteorological drought prediction by using the genetic programming approach and uncertainty analysis using the Copula.
Can you increase your voice, please? Maybe through your speaker. Yeah. Okay. No, still it is.
Calculate the SPI index according to the info. drought prediction model by the SPI index and ocean. Drought is the of the water and its temperature. Logical dot with SPI index. What would be just come under in this revision? So an AO for the answer. Oh. The uncertainty analysis with joint distribution, marginal distribution, and the cumulative distribution function. Steps involved in this the dot SPI is a dimension versus the info the index and which is multiple times here, and this dimension is value should to calculate the the dot categorized in SPI index based on the negative value. This is one simple example of the how SPI indexes work. If the rainfall is take place, there is rise and limited rainfall is not present, the drought condition is arise. The advantage of SPI is the minimum data required, quick we can sample and calculate the varied time scale, and it can give the early warning and the drought severity. The data required for the GP prediction model, the oscillation patterns ENSO Equino IOD is collected from the SRL website, and the monthly rainfall data is collected from the IITM from the 1871 to 2016. Out of that, 1951 to 1918 data is used for the training purpose. 1981 to 2000 data were used for the validation purpose, and the data from the 2001 to 2016 is used for basic based on rainfall index is the annually also used for the prediction of this genetic programming model, and climatic indices are there which used for the prediction model. And output is the 1 month lead time drought in terms of SPI index. It will
Ajay, please try to wind up. It is too much. Yeah.
This is a model. This is a combination of the model. One of the combination of the combination. 14 models are created. Out of that, 14 number C14 model is the best for the prediction of this drought. The 14 model where SPI index in a 6 and that instant and results. Out of that, the 14 number model is having the best result for the north, where training values were observed 0.7 and testing is 0.6. For the west central region, 0.85 and 0.73. This that compared to the. This is the basic chart of the GP prediction model for the training as well as the testing purpose for the Northwest region. It can be observed that the most of close in training as well as uncertainty analysis using the copula. In this, this is divided in 4 steps. First, comparing this observed and predicted dot copula, selecting the 6 functions. Then MCMC simulations is applied for the posted distribution to calculate the answer. This is the outcome of the uncertainty analysis of the Northwest region, where dependence between the observed and predicted dot is calculated by Kindle, rank, and Spearman to obtain and 5% is also calculated. And Gaikwad is 5% the margin distribution for the Foster distribution of the MCMC analysis, and for the selected 6 copula, out of that, on x-axis is represent the parameter value and the values derived from the parameter.
Please finish, please.
Yes, sir. This is for distribution of the parameters with the uncertainty and with the very NSE values. Similarly, analysis for the West Central region is calculated, and this is the result. This is the final result of this region. The conclusion: the between the large scale atmospheric circulation patterns can be calculated by using the meteorological drought prediction. Genetic programming approach used to capture the complex relationship between the drought prediction model, and the observed and predicted events are the nearly matching, and it can be used for the mitigation plans.
Okay. Thank you, Ajay. Thank you.
Okay.
So, Dr. Dula, now we will invite Dr. Dulal Chakravarti for his talk. So, a simple multilinear convolutional neural network model. So, please, Dr. Chakravarti. Yeah. You share your presentation, sir.
Sir, please firstly open your PowerPoint, then you share it.
Yeah. Ajay, please unshare your screen, then.
Okay.
Dr. Dulal Chakravarti.
Dulal, sir.
He is unmuted. I don't know. He is there. Yeah.
Just
Yeah, please.
can you hear my voice?
Yeah, I can hear your voice, but there are no presentations. Please present your. Yeah.
Okay, just 1 minute. The screen is visible.
No.
1 minute.
Your screen is visible. Yeah, now fine. Yeah, please. No, again. Start your presentations first on your screen, then it will share.
Yeah. Is it visible now?
Yeah, it is visible. Fine.
Okay. Thank you,
Yeah.
Mr. Chairman, and good afternoon to all of you and distinguished delegates. I present a simple multi-layer convolution neural network model for classification of clouds from inside cloud imageries. My objective is to build this model using Python and Microsoft Cognitive Toolkit, which is an open source package. Data for this model is collected over the surface observation network of IMD, which is shown here with the cropped image segments superimposed. You can see the inset where I have shown a magnified view of the image segment over port bare observatory. CNPK, which is the brief form of Microsoft Cognitive Toolkit, data is processed in the form of text files. As you can see down below the slide, labels are on the left, which is a vector of length 4, indicating one of the low, medium, high, or no cloud conditions, or no cloud types. And on the right are features, which is a tuple of 6 by 9 by 9 pixel integer values. 6 means that is the number of channels, and 9 by 9 is the width and height of the image. Model processing involves downloading of the image data from 3DR and 3D satellites at 6 UTC plus minus 15 minutes, and also surface observational data of 6 UTC. Pre-processing includes georeferencing of all the images and decoding of the cloud groups. Out of this image as well as the observational data, we create a CNTK data frame, extracting image values as well as the observed cloud type. Many such CNTK data frames constitute what we call the data set, which feeds the model with 3 convolution layers in our case. And once the model is trained with the data set, we use the weights and biases of that model to predict the unknown cloud class type. Core concept in the CNN model is the convolution operation. We define here 2 containers, X image values of 6 by 9 by 9 dimension, and Y, the output vector of length 4. Convolution involves scanning by filters of the images, performing the dot product operation between the image and the input values. And bias is added to this dot product. And the sum of these two is optionally mapped through a nonlinear activation function to give the output of this layer, which becomes input for the next layer. Many such layers stacked in tandem produces the final output. And this is the concept of the deep learning architecture. CNN model is built with configurable hyperparameters. An instance of that model is created, in our case, with 3 convolution layers of 8, 32, and 128 filters, with ReLU as the nonlinear activation function. These are followed by a dropout layer with 20% node dropout to prevent overfitting, and a dense layer which fully connects to the 4 output classes. We use 8 parameter tensors and 81,244 training parameters. A small set of observations called mini batch is loaded into the model, and then the average error from that set is used to update the model parameters using stochastic gradient descent. When after thousands of operations, the average error does not change significantly, we say that the model is trained. And these trained models, weights and biases are actually used to predict the unknown classes. One important parameter we found in our case is the learning rate, which when is reduced, and it is actually to be optimized for the best result. We use 25 unknown samples of cloud image, and we find that when the model learning rate is reduced from 0.13 to 0.1, the accuracy changed from 60% to 80%. So to conclude, we say that we demonstrated a model, CNN model with 3 layers, which can predict unknown cloud types with reasonable accuracy. Model can be improved by changing feature size, level size, number of convolution layers, and the learning rate. Insert, some applications could be insert program has more than 30 years of image data, and a grid point cloud climatology can be developed over India and neighborhood with good temporal and spatial separation. The model, it is of general nature, so it can be used to classify clouds from Doppler weather radar images also. Actually, this type of model can also find application to classify severe weather clouds like storm clouds as well as the heavy rainfall clouds. I acknowledge with thanks the IMD ISRO rapid portal for the INSAT images and the WMO information system portal agency for the surface observations. Thank you, Mr. Chairman.
Thank you, sir. It is in its future applications, because gridded data has been generated, as I remember, by Mahakur of Indian Institute of Tropical Meteorology and something like that. So that can be used. Okay. So it is very nice presentation, sir. Thank you, sir. So now I will invite Miss Isita Sarkar. She is there. Isita Sarkar.
No, sir.
She is not there.
She is not there.
Okay.
Next one is
Then
Preeti.
Preeti. Yeah. Preeti Tahlani.
Yes, sir. I'll
Okay.
share my presentation. Good afternoon. Are you able to see my screen? Good afternoon, Chair and Co-Chair. Today I'll be presenting my work on use of machine learning and drought prediction in Indian scenario. I'm from Mahalanobis National Crop Forecast Center, which comes under the Ministry of Agriculture and Farmers Welfare. So drought is a very complex phenomena. It depends on many parameters, and currently only drought assessment we are doing in our country. There's no system for like for some early warning or prediction system. Our center MNCFC carries out agricultural drought assessment and monitoring. Agricultural drought assessment and monitoring for 17 major states of the country under the National Agricultural Drought Assessment and Monitoring System. So only drought assessment we are doing, and it is based on the Ministry of Agriculture during 2016 has published a drought manual. So we are following the methodology. Initially, the methodology was given by the technology was given by ISRO and operationalized at MNCFC. Earlier that we were using, but after that it was improved and a drought manual was published and a methodology was given. So drought assessment is done as per that methodology. So there's no early warning system. So in this study, the aim is to explore the use of machine learning techniques in any given area. So my study area selection, I have selected study areas around 10 to 11 districts of the country I have selected, and I have selected based on the different climatic zones of the country. On the left side, you can see the moisture index based climatic zones, like the country is divided into per humid, moist. So from every zone, I have taken 1 or 2 districts. So these are my districts: Kathal, Jalore, Surendranagar, from different regions. So basically drought is affected by many parameters. These parameters are also laid down in the drought manual, which we currently used for assessing drought in any given area. So we are using rainfall, vegetation condition, temperature, soil moisture, and hydrological condition. So these are the factors that affect any given area for drought. So here in my study, I have selected 2 parameters, rainfall and satellite-based NDVI. My reason to select these 2 parameters is the availability of data, since machine learning techniques need large amount of data. We don't have soil moisture data, hydrological data since so long. So I have used these 2. Rainfall data I have taken from IMD 1989 to 2019 at district level, and NDVI data already at MNCFC website we are uploading 2006 to 2019 NDVI data, and from MODIS I have processed from 2000 to 2005. So that way at least I have got 20 years common data, 20 years data for rainfall and 20 years for NDVI. So this is my input data. So I have taken the this blue one is the rainfall and red one is the NDVI, and yellow lines are showing the drought occurrence. So this drought occurrence is taken from the information is taken, sorry. This drought occurrence information is taken from the Ministry of Agriculture website. So whenever those districts have been declared drought by those states. So this is the drought information. So I have used following this study has been carried out in Python. I have used Python for this.
So different algorithms I have tested like logistic regression, k nearest neighbor decision tree, random forest, SVC, and finally the multi-layer perceptron. And I have validated those models using different performance metrics, accuracy, precision, recall, F1 score, area under ROC curve, and confusion matrix. So implementation, I have used sklearn in Python, and I have used cross validation for training my models. So 80% data is used for training, 20% for testing. Out of this 2000 to 2019 data, 16 used for training and 4 used for testing, and cross validation is done. That means every time one set of 16 is used for training, other 4 for validation, then again 16 set for training and other 4 for validation. So my predictor variables were rainfall and NDVI, and predicted variable was the drought occurrence, whether that district had drought or not. And then actually this study I had done before the monsoon season of 2020. So I used ARIMA model for predicting rainfall and NDVI, and in turn predicting drought for 2020. And now I'll be showing the results. Okay. So for example, if I go to Dhule district, so for Dhule district, almost all, what I found that almost all the algorithms are giving the perfect result. Here we can see that we are having the accuracy, F1 score, precision, recall, all leading to 100%, and ROC curve also is having the maximum area under it. So that shows that all the algorithms are, and this is based on the cross validation which I have done. Like every time 16 were used for training and 4 were used for validation purpose. So from that curve is built. So this is the rainfall. This is the rainfall. This is the NDVI curve, and these are the predicted. And here you can see the confusion matrix also. So in this case, I am getting all the prediction as correct ones. Then I tried for what will be the value for 2020. So for rainfall and NDVI, I used the ARIMA model to predict the rainfall and NDVI, and based on that, these all parameters gave as no drought condition. But now, since after the monsoon season of 2020, I had the NDVI and rainfall for this region, and using that again, I ran the same model which I had built. So these models gave the as no drought. Similarly, this is Jalore district from Rajasthan. So for Jalore district also, these are the this is the performance.
Please finish in 1 minute, please.
Okay. So these are the similar results for Jalore district. So here also I am getting no drought condition for the 2020, and same from the actual data also, and for Bagalkot. So I'll come to conclusions. So in this study, a framework for drought prediction is built based on machine learning. So better performing algorithms that I found based on accuracy and F1 score are logistic regression, random forest, support vector, and multi-layer perceptron. And they can be used for an early warning system, this framework. And we need more data to train the model and get proper predictions. And more predictor variable can also be included, like soil moisture, temperature data we can include. And normal rainfall, currently I have built different models for different districts. But what we can do, we can use the normal rainfall and normal NDVI over a large period, and we can try to prepare a generalized model for all districts. So I acknowledge my colleagues, my center.
Thank you. So do you see some trend in NDVI? Because I have seen that every
Sir, your voice is breaking.
Oh, sorry. Is there any trend in NDVI?
Yes, at some places we are getting some trend, but not much. Actually, it is depending on rainfall also, what I have observed. So since the vegetation condition, whenever the rainfall is good and NDVI is picking up the greenness, so whenever the rainfall is good, the NDVI will be higher. So that way I am seeing a relationship.
Yeah, but I have seen that mostly NDVI is increasing whether rainfall is increasing or not, because there is no trend in rainfall, but NDVI is showing some trend.
Yeah, because actually, sir, that NDVI which I am showing is for majorly for the agricultural area, because our center is focusing on mostly on the agricultural area. So what is happening that many areas are every time they are irrigated also. So that's why a trend is there that every time it will increase. So that is also one of the reason.
Hello?
No, sir.
He is not there?
Hello.
Yeah, I am here, sir. It is a very nice presentation.
Yeah, now you take other presentations also. Dr. Dibyajyoti, you take other presentations. So you take other presentations. Rest there are more 3 presentations. So you invite
How many
people.
are there?
3 more.
Okay, sir.
So you invite other next one, or I should invite?
Sir, you invite. I am having some issues with my system.
Okay. So next presenter is Amarendra Singh. So I invite Dr. Amarendra Singh for his presentation, if he is present. Amarendra Singh. Hello.
And then while logging in, there will be an option for app probably. So, so that app you log in.
Yeah, Amarendra Singh is there or not?
No, sir, not present, sir. Not present.
Okay, then Venkatesh Gowda.
Yes,
Dr.
sir.
Venkatesh Gowda.
I'm sharing my screen, sir.
Okay. Thank you. Please.
Is it visible, sir?
Yeah.
Good afternoon, one and all. I'm Venkatesh Gowda from CSIR Fort Paragon Institute. Today I'm here to present the convolutional neural network used for LUSC classification. And here, sir, I am getting this screen. Okay. The main objective of our work is that designing the convolution algorithm for classifying the RGB composite linked images for using Sentinel-2 satellite. We are estimating the overall accuracy and entropy loss for RGB band composite images, and we are testing the sensitivity of the hyperparameters for improving the overall accuracy of the image classification, and we are also presenting the class-wise performance of the classifier. The main motivation to choose the LLC classification is many of the researchers in the remote sensing field using land use land cover classification in different applications like urban planning, historical LLC conditions, and agriculture fields. CNN has the inherent capability to extract the features from the training samples, and it can train by itself. Here, I'm using the Eurosat data, which is publicly available for land use land code classification, and this data contains a total of 27,000 RGB composite images with 10 different classes, and the images are all images are georeferenced. These are the sample images of which are used for classification purpose. Here we have 10 classes like annual crop, forest, agriculture, vegetation, highway, and industrial pasture, permanent crop, residential, river, and sea lake. Here we are dividing our total data into two sets, training set and the validation set. We are using 80% of the images to the training purpose, and we are using 20% of images for the validation purpose. This table shows the number of images with respect to the classes for training and validation. In total, we have 20,000 images we have used 20,000 images for classification. The methodology, here we are using three-dimensional input is fed into the convolution layer. Here NH is the height of the image, NW is the width of the image, and NC represents the number of channels or depth of the image. Like we can see we can also say that the number of bands of an image. Here we are using RGB 3 bands, and the corresponding output is shown here like NHL, NWL by NCL for n number of layers. As I told, we are using deep learning based convolution neural for classifying the multispectral images. And this study proposes 5 layer basic convolution neural network with ReLU as an activation function, pooling and regularization as dropout, and fully connected layers. The convolution layers and pooling and output layers are associated with the weights and biases, which are formulated as follows, and the activation function is represented as follows. And in this work, we have used ReLU activation function for convolution and fully connected layers. Since we are using the multi-class classification, we are using softmax function for at the output layer. This model, this is the block diagram of the proposed model. We are giving input in the structure in the 3-dimensional 64 by 64 into 3. 64 is the height and width of the image, and 3 is the number of bands. And we are giving these images into the convolution layer. After the convolution layer, the output of the convolution is passed to the max pooling layer. And at the end of the convolution layer, we have flattened the output of the convolution to the one vector values, and this is fed into the fully connected layers with the dropout, and we will get the 10 different values with respect to the classes. Here, hyperparameter tuning plays an important role in improving the performance of the classifier. By looking at the training set error, we would know how well we are training or how well we are fitting our training data. If our algorithm has high bias, then we are underfitting the data. If we have high variance, we are overfitting our training data. And other hyperparameters like batch size, evokes, optimizer, learning rate are fine-tuned for this classifier. To reduce the high bias and high variance, we use the following method. If you have high bias, we use a bigger network, and we will go for training the classifier for longer time. If we have high variance, we'll use more data for the classifier as an input, and we use regulation techniques like dropout, L2 regulation. And we have using dropout regulation in this classifier. Overall, we achieved an accuracy of 96.37% by using an n-atom as an optimizer at the 0.00012 learning rate. And here in this graph, we can see the upper portion is the training loss and training upper portion is the training accuracy and validation accuracy, and lower portion is the training loss and validation loss. Here the cross entropy loss increases as the predicted probability diverges from the actual label. Here it shows the confusion matrix of the classifier. Here the diagonal values represent the each class accuracy. As we can see, the residential has the highest accuracy of 1 by classifying all the residential images as residential class, and we have industrial as 0.89 accuracy, which is the lowest one, because 11% of the industrial images are classified as the residential images. This is the precision table for classification problem, and here we have three different performance evaluation matrices parameters like precision, recall, and reference score. Precision tells us the what portion of the positives are actually actual positives, and recall tells us the what portion of the actual positives are correctly classified. F1 score is nothing but the harmonic mean of the precision and recall. Support is the number of images used for the validation purpose. Conclusion here, by using we have achieved 96.37% of accuracy by using NADAM as an optimizer, ReLU as an activation function at the learning rate of 0.00012, and by seeing the confusion matrix we can see that residential and forest are performing well amongst all the classes, and the industrial class is a low performing class because some of the industrial class images are treated as or misclassified as residential images by the classifier. In the future work, we can use multispectral band images instead of RGB composite images to improve the accuracy, and we can also use pre-trained models like GoogleNet, VGGNet, or there are many architectures to improve our accuracy of the classifier. These are the references which I have used, and I would like to take this opportunity to thank NMHS for funding the project, and I would like to thank Dr. KV Ramesh and Dr. Rakesh for guiding me throughout the work, and I would like to take this opportunity to thank Tropmet for accepting my paper and allowing me to present this work. Thank you so much. Hello.
Thank you very much. Why have you not used multispectral data?
We have used that as for future work, and we are trying those images now, sir.
Okay, so means you are getting better result, or just
hopefully we are getting better results compared to the RGB data, sir. Composite images.
Okay, good. This is a very good work.
Thank you, sir.
Okay. So now the last presentation will be from Kiran Kumar. He is present there. Kiran Kumar.
Hello, yes, sir. I'm audible.
Yeah, yeah.
Yeah,
please.
like now I am sharing my
screen.
Good afternoon to one and all. Like here I'm presenting the Indian summer monsoon rainfall prediction using the deep learning algorithms called the LSTM. So the main objectives of my study is like developing a deep learning algorithm to predict the Indian summer monsoon rainfall, and like to know which are all the indices which are significant in predicting the ISMR, and to find out that I am using the multipolarity and the correlation coefficient. And next is the performance of an LSTM variants in predicting the ISMR. That is, we are using the two types of an LSTM variants, that is a standard thing and a bidirectional. And at last is we are testing the sensitivity of the model using the hyperparameters tuning in improving the overall accuracy of the rainfall prediction. Like what makes us to select these studies, like the prediction of an Indian summer rainfall is at the heart of a tropical climate prediction, despite the enormous progress having been made in the predicting ISMR since 1886. As per the like previous studies, they are having a limited skill in predicting. Like their forecast skill is around 0.51 for 1988 to 2012, and a 92 years retrospective forecast skill of 0.64 for the other year. And also we know that like this ISMR, it covers annual rainfall of around more than 90% of a central and western India. Then about 65% of our total cultivated land in India is dependent on the summer monsoon only. And why we are using the long short-term memory is like it is one of the special kind of an artificial intelligence, and it is superior compared to other models in the artificial intelligence. Like it is a deep learning model with a large margin of time series predictions. Like it has a special ability to learn the long-term dependencies. The next comes to data. data like we are using around 118 years data from 1901 to 2018 of an ISMR. Like other exploratory variables includes like other indices over global circulation indices like Southern Oscillation Index, Nino 3.4, North Atlantic Oscillation, and the Dipole Mode Index. That is the Indian Ocean Dipole Mode Index. And in this case, the like data is split into a test and training set with respect to 80% to 20% respectively. And here the graph it is representing the relationship between the ISMR and an HOI. Like this blue graph we can see here, like it is representing the positive relation, and here the Nino 3.4 that index is here we can clearly see that it is a negatively relating. The next comes to any variable identification. Here we are using the method called the multicollinearity. What the multicollinearity is like? So among the explanatory variables, there is a chance of presenting the linear, they are linearly related, or there is a chance of correlate among themselves. So to identify the related variables, like we are using the multicollinearity. For that method, we are using calculating the variation inflection factor. That is a VAF value. We call it a VAF value. Those VAF value below 9, we are selecting for the model. So in this case study, like in our study, like we are selecting the VAF value less than 10 to build the model. And like we can see here, Nino 3.4 VAF value is we are getting the 49. But as per the previous studies, we know that Nino 3.4 have a significant role in predicting the ISMR. So that's why we are retaining the Nino 3.4 in our study. And in the correlation coefficient columns, like you can see the correlation coefficients which are having the significance level of 5% and 1%, like we are using in our study. And these significant variables are selected based on VAF and correlation coefficient value. And this is like this chart is a correlation matrix. We call it a correlation matrix. This explains that the correlation between the ISMR with respect to all other indices. Like here we can see that the rectangular boxes shows the strength of the correlation, and this color indicates the direction of the correlation. These four indices are like selected based on the correlation matrix. Like here clearly we can see ISMR how it is correlating with other exploratory variables. Then next comes to an approach. Like we are using the LSTM in our case. Like what is an LSTM? It's a long short-term memory, which has an ability to learn on the long-term dependencies, or it can store the information over a longer period of a time with the help of a special structures called as gates. So that's why it's called as a gated cell. Now here you can see that the straight line where the information carries all along the process. Like these cells, this will present in the hidden layer. The operations, like I will go into explain now the operations in the LSTM cell. Now first is in a forget gate. Forget gate, what is explained is it will forget the information which is unnecessary information, like we can call it as a noise. It will forget the noise information. The next comes to an input gate. What it is do is like it is update and retains the information what is required to move to the next cell. The next comes to an output gate. In the output gate, like it carries the information related to next cell. The output from this cell, we call it as an output of the cell. Similarly, that what I am explaining, these are mathematical equations of the process in the LSTM cell. Then next comes to the methodology. Like what we are doing here is like we are using two kinds of an LSTM variants. One is the standard and bidirectional. As I said, the bidirectional LSTM are the extension of described LSTM. Previous, like at the first LSTM is applied on the input sequence. That is first the moving forward is known as an forwarding, and then the bidirectional LSTM. What is happening is like then the reverse. The input sequence is read reverse. The reverse form of an input sequence is fed into an LSTM model. That is called the backward layer. Now applying the LSTM twice leads to improve the learning, long-term dependencies, and thus consequently will improve the accuracy of the model. Now here I am going to show that schematic representation of an methodology. Like here first we have a time series of data. Then we are with the data, like we are selecting the significant factors for the model. Then we are dividing that into a train and test data set and a scalar and making the scalar transformation. And we are preparing the divided data into an input matrix which is suitable for the model buildings. Then this prepared the input sequence, like input layer data, which is subjective to two types of variants. One is the standard LSTM, and one is the bidirectional LSTM. Then the standard LSTM, as we discussed, the LSTM says all the process like forgetting thing and updating thing and the output to each cell that will happen. Then from that output of that model, which is then that we are using the test data using to validating, and we are recording the error values. And similarly happens in the bidirectional also, like in the bidirectional, which is in feed forward and forward direction and bidirectional and reverse direction. It will take in the two directions, and we are using that model output, and we are using these two model outputs to calculate the errors like RMSE, MAE, and MAPE, which means that root mean square error, mean absolute error, and mean absolute percentage error for the result visualization. So after the result visualization, we are comparing the performance of these two variants. Here comes the results. One is in root mean square and in mean absolute error. Here you can see that root mean square error of a standard thing and a bidirectional clearly. The green trends explains the standard things, and the blue trend explains the bidirectional thing. These four are with respect to four different batches. Like as the previous presentation, we can tell that it is a sliding window technique. Then comes to mean absolute percentage. Here also, like fifth node, this the x-axis here explains the number of nodes we are using for the model building. Then hyperparameters, we are using like 2 to 15 different nodes, how it's performing to check that one only we are using. So from this results, it is clear that the fifth node and the ninth node, we are getting the better results. Then when we compare these two nodes, fifth and ninth node of a different variants, like here we have two scenarios. First scenario is in a train and test. It is like we are not fixing any train to any test set. That is a shuffled case. And the second scenario is in a fixed case, where we are fixing the certain number, like 80% of a data into a test case, and the last 20% of the data into a test case, and first 80% of data into a train case. So here it is clearly seen like bidirectional LSTM is performing better within a minimum RMSE, MAE, and MAPE value when compared to a standard, and in the case of a fixed standard and bidirections. So overall reduction percentage in the bidirectional LSTM with respect to a standard LSTM, you can see around 20% in case of an fifth node, and around 22 to 23% in case of a ninth node. Then comes to an actual versus predicted graph. So so overall 80% is divided into a trend set. Then after, like we are testing, we are predicting, and we are comparing with an actual. Here the green graph, it is in a predicted within a fifth bidirectional LSTM model, fifth to 5 nodes, and this one purple line, which is explains in a bidirectional LSTM predictions with 9 nodes. So clearly we can see that the fifth node is performing better than compared to a ninth node. Then this is the graph of comparing of a loss of the two different nodes in a bidirectional LSTM variant. So we are like a fifth node. It is the graph, the loss graph is clearly seen that at some point the two training loss and the validation loss, they are going to stabilize, and in the case of a ninth node, like a 250 epochs, we are using the 250 epochs here. Like at the 250 epochs, we are not meeting at the point. Like we can, if we increase to a certain number of epochs, there is a chance of getting stabilizes and get touch at some point. So the overall conclusion is like bidirectional LSTM found the superior than the standard LSTM with an average of an 18% reduction in root mean square error, 23% reduction in mean absolute error, and overall 22% reduction in MAPE error. When we are comparing among the nodes, like fifth node and a ninth node, here an average of a 5.4% difference in the error reduction of the fifth node to the ninth node. Like using the predictors having the VAF value less than 10 or statistically significant will result in improving the model performance. And we can also tune the hyperparameters like hidden nodes, dropout, activation, optimizer, batch size, and the epoch size. So by tuning these, we can get a more accurate model, and we can reduce the error much. So these are all the references. So like at this moment, I would like to thank the NMHS for funding, and I would like to thank Dr. K.V. Ramesh and K.V. Rakesh for this.
Thank you, Kiran. Can you tell me, have you compared your results with simple multiple regression?
So like after we are getting the fine-tuned model, we are planning to compare with other physical and empirical models and other
but you have taken this bidirectional model and with 5 nodes, you are getting 7 points something more than 7% error.
Yes, sir.
So it is very more than a half, almost 70% of a standard deviation. So
Yeah.
your model is not better, I think, than the multiple regression model. If you use the same variables in multiple regression,
Like as it is a deep learning model, sir, like we are planning to run for the different type combinations of the hyperparameters. Once we get the fine-tuned model, then we are planning to compare with the other models, sir.
but
after fine-tuning,
think
we are
on that because it is not performing great. So you have to think on that. Okay.
Okay. Thank you, sir.
Okay. So Dr. Dibyajyoti, you want to comment on the whole session something?
Yes, sir.
Yeah.
Thank you, sir. Thanks to all the participants for nice and informative presentation. Nothing much to say, sir. Just to say congratulations for your fantastic efforts. All the best. Thank you, sir.
So with this, this session is ending, and we thank all the participants. And first, I would like to thank Nachiketa because he has given very nice lead talk. And after that, also the talks were very good, and good effort is being done in utilizing artificial intelligence in different field, from cloud classification to land use, land cover to rainfall prediction to other things. So it is very nice that we are moving towards the data-driven models, and there is some promise in that. So thank you all.
Thank you, sir.
Thank you, sir.
Thank you for chairing the session. On behalf of IMS Shillong chapter, I would like to extend my thanks to Sir Dr. A.K. Sahai, senior scientist from IITM, and Dr. Dibyajyoti Chutia, senior scientist from NESEC, for nicely chairing the session and finishing it well within time. And we are also thankful to the lead speaker of this session, Nachiketa Acharya-ji, for giving the different aspects of AI, artificial intelligence. We are thankful all the participants. With this, we come to the conclusion of today's technical session. Now we will start our last session. Before that, I would like to request the chair and co-chair, sir, kindly send the evaluation sheet based on that.
Yeah, I will send. I will send.
Okay, sir. And one more thing, sir, from this session, if you can give some takeaway point for recommendation, as we need it for the final recommendation. So it will be helpful, sir. So you can mail it to our organizer.
Okay. Okay. Thank you.
Thank you, sir. So from 4:30. Yeah, 4:30. So 4:30, we will have our popular talk by Dr. Shailesh Nayak, Director, National Institute of Advanced Studies, and former Secretary MOES. And the talk will be in the Himalaya Hall only. So I would like to request all the attendees, participants, please join us for the popular talk at 4:30. Thank you.
Request Patnaik sir to.
Thank you. Thank you very much.
And also I'm requesting Patnaik sir to kindly introduce sir, moderate the
Okay,
session.
yes, sir.
Thank you, sir.
Thank you very much.
video.
Hi, good afternoon.
Namaskar, sir. Good afternoon.
Namaskar. So how things?
Yes, sir. Fine.
I don't see many participants here.
Sir, sir?
There are not many participants I could see here.
No, sir. Here, this is the panel group. So only here, few people will be there.
Okay.
All the participants are through different, that means around 300 people are attending.
Oh, okay. So this is only special for those who are
Yeah,
going to speak.
means who need to share this PPT to the
Right,
panel,
right, right.
panelist.
Okay.
And DG sir also will join because I just now he was informating. He said he will join. Initially we were thinking how it will happen because 3 days, 4 days, but it is going on very well.
Good, good. Very nice.
Namaskar, sir.
Raju, how are you? Good to
I'm
see
fine,
you.
sir. I'm fine, sir.
Yeah, very nice. So, it's not cold there in Shillong?
Yeah, it is cold. Some inners are there.
Here you put heater on, huh?
Yeah, yes.
It's quite cold now, no?
Yeah, it is cold now. Today is, I think, more colder.
Today's cold, no sunlight.
No sunlight.
No sunlight also.
Yeah, I'm remembering, sir, first we started this Tropmet at IERS in 2012 under your presidency. And then Patnaik also was there. You were that time Joint Secretary or Treasurer?
Muted.
You are muted.
I was executive council member, but I was fully involved with the team.
Correct. Yeah.
But really, after that, we have not looked back. It is progressing very well.
Yeah, no, it is going very well.
We also this organizing using a professional PCO, sir. So in a 3D environment.
Okay. Good. Yeah, you have to do that now because it should appear as if it is like normal conference. So that will help us.
Yeah. No, they have done very nicely. They have given four parallel sessions, 3 technical sessions, 1 for exhibitions.
Okay.
So we also arrange exhibits through online. Around 13 exhibitors are there. So more than 500 registrations were there. And total 312 presentations, including 232 oral presentations, 112 poster presentations. And then for the posters also, we have given a 3-minute video clip, so that quickly somebody wanted to get summary of that, what this is done.
Yeah, so it is happening almost as if normal conference, except
सब तो आ चुके हैं, सब आ गए हैं।
physically present.
हो जाएगा। सर I just हम डिस्कस करें ऐसे राजू सर है।
After I am coming to that Bangalore, no sir, I think January I did not move much. That advances in geospatial technology, that NIAS which was organized, it was very nice.
January, this year, January.
Yeah, this year, January, sir, correct.
Yes.
Yeah.
So after that, all this started now. So
Yeah, March onwards is actually started. After 1 month,
I've
it has.
also not gone out by last March. So 9 months I've been here only.
Oh, right, right, sir, right.
But now I find unnecessary wear clarity. I'm very comfortable.
Yeah, sir. Yes. Sir, actually, Tropmet, now more people are attending compared to when we are under physical.
Yeah.
So, that is the advantage.
Yeah.
Acha, Raju sir, Mahapatra sir is connecting, I think. So, if there is anything you have to give, that just see.
Yeah, he has not yet joined.
No, he has
Not yet.
not
Joining.
I've already messaged.
Okay.
Whenever
Acha, no, he will join. I talked now. He will join.
so all the this technical session in all the halls are already over, so no problem from there.
Okay, so all the halls are over na time.
Yeah.
Yeah, morning specifically I had told them to make. Sir, yeah.
Sir has come.
Sir,
namaskar.
Namaskar, Mukherjee. How are you?
Fine, sir.
Fine. All well?
Sir, thank you very much, sir. You have agreed for this.
Yeah, yes, sir. Yes.
Session and deliver this memorial lecture.
Agreed, but I am not sure whether you will be very happy after this. Not my expertise, right?
Sir, you are the role model for each of us, sir.
Experts in weather and climate.
Sir, it is popular lecture. People will enjoy this. They will like.
I have made it little simpler so that not talking about actual weather forecasting, but how this satellite has been able to do this.
4:30, no?
So we can start, but now.
I think we can. Yeah. So all the sessions are already over. So we can start. Nee, Rajuji, we can start, na?
Yeah. Sir, one is through this website. Another is we are also kept this under YouTube link also.
Okay.
So that is also there. Yeah. Yeah, you can start. Patnaik, you please unmute.
Yeah, we are live there. So let us start the session.
Yeah, please start.
So good afternoon to everybody. So this is a popular lecture series. We have kept one, and this will be delivered by renowned scientist Dr. Sailesh Naik. He was the secretary of Ministry of Earth Science, and also he was earlier worked in the DOD and INCOAS. So before I will request our Mahapatra sir, our DG IMD and President IMS, to elaborate more about the Dr. Sailesh Naik sir. Please.
So good evening, namaskar. Respected Dr. Sailesh Naik sir, Director, National Institute of Advanced Studies, and former Secretary, Minister of Earth Sciences, distinguished delegates, ladies and gentlemen. I am glad to inform that Dr. Sailesh Naik Saab has kindly agreed to deliver this popular lecture on recent developments of remote sensing in weather and climate applications. As all of us know, India and South Asia is such a part of the world which is surrounded by the mountains like the Himalayas and the oceans like the Bay of Bengal to the east, Arabian Sea to the west, and Indian Ocean to the south. So naturally, the South Asian region, and especially India, becomes a data sparse region. However, with the advent of the satellite era in 1960s, and with the introduction of the satellite by India in 1980s, the country has made a quantum jump with respect to the remotely sensed observations to enable the better monitoring, prediction, and warning services with respect to them. The remotely sensed observations initiative taken up by India has helped not only our own country, but also the entire region, South Asia, Southeast Asia, West Asia, Middle East. And also these data are exchanged with various countries in the globe. And we are a part and parcel of the remote sensing family of the globe and also the satellite family. Dr. Shailesh Naik is a well-known and renowned scientist. He is known to each and everyone participating in this event, but still, I will take this opportunity to introduce Dr. Shailesh Naik sir with a few of his achievements in this field of science. Dr. Shailesh Naik is currently Director of National Institute of Advanced Studies, and he is the former Secretary of Earth, Minister of Earth Sciences. He was also the Chair of Earth System Science Organization, and he provided leadership for the programs related to science of climate change, weather services, polar science, geoscience, ocean science and modeling, ocean survey, resources, and technology. Dr. Naik obtained PhD degree in geology from MS University of Baroda in 1980. He joined the Space Application Center in 1978 as a scientist and subsequently elevated as the Director of Marine and Water Resources. He was mainly responsible for conceptualizing, formulating, and executing many national level projects related to application of satellite data on ocean color, integrated coastal zone management, snow and glacier studies, and water resources, and developed potential fishing zone services, which is directly related to socio-economic development of the country. Dr. Naik was appointed as Director, Indian National Center for Ocean Information Services, Hyderabad, under the Minister of Earth Sciences in 2006. He set up the state-of-the-art early warning system for tsunami and storm surges in Indian Ocean, which is now being applied by many countries in Asia, Africa, and island nations in the Pacific and Indian Ocean. He was responsible for conceptualization and development of the marine GIS. He made outstanding contributions in improving the advisory services related to ocean state forecast and Indian Argo project. Dr. Naik is the chair of the National SCAR Committee, Indian National Science Academy, New Delhi, Research Advisory Committee of many institutes, and by that way, he has helped in extension of scientific research and applications to the society. Dr. Naik is the fellow of Indian Academy of Science, Bengaluru, the National Academy of Sciences, India, Allahabad, the International Society of Photogrammetry and Remote Sensing, ISPRS, and academician of the International Academy of Astronautics, Paris. He has been awarded honorary degree of Doctor of Science by Andhra University, Asa University, and MIT University. Dr. Naik is recipient of many awards, including Mariner and Lifetime Achievement Award, Geosciences, ISCA Vikram Sarabhai Memorial Award, Oscar Award. He has been awarded with Lifetime Achievement Award for India Geospatial Leadership for outstanding contribution to development dissemination of geospatial technology in India. He has produced many PhDs, and hence the young talents in the country. He is the president of the Federation of Indian Geoscientists Association, Indian Geophysical Union, Indian Society for Remote Sensing, and Indian Mangrove Society. He was the president of the International Geological Congress and many other bodies. Personally, I have been blessed with Dr. Shailesh Naik sir, with his valuable guidance and advice as Secretary of Minister of Earth Sciences in helping to improve the weather and forecasting services in general, and also the cyclonic services in particular. I will never forget, sir, your guidance and best wishes and blessings towards the improvement of the services in the country and the region. And we are still getting this guidance, and we hope we'll get your guidance in future also. So it is an honor for Indian Meteorological Society to request you, sir, to deliver this popular lecture on recent developments of remote sensing in weather and climate applications. Thank you very much, sir. I now formally request you to deliver your lecture.
Thank you, Dr. Mahapatra. I'm extremely grateful to Dr. Mahapatra, Dr. Raju, and of course, Tropmet for inviting me and giving me this opportunity to talk to you about the variety of services which now is providing and what is the actual role of remote sensing in this. Actually, in our country, the first satellite data was acquired by IMD way back in 1965. That time, Giro's data satellite was launched, and we used to get images. And so I would say that IMD has been using for the last 55 years the satellite data. And today the situation is such that the satellite provides very vantage position to observe the Earth. And that is what we have been doing. Actually, if you see this, that forecasting, weather forecasting is essentially whatever knowledge which we have about the Earth system. Based on that, we try to predict the conditions in a particular place or particular time. And this is possible because of the various quantitative data which we get, not only about the atmosphere, but also about ocean and also about snow and ice, land surface, many others. So basically, the whole system is based on the observations. How well, if you can observe, the better your prediction would be. So my talk, I am trying to tell you about some of the major things which satellite has been providing information and how best this has been made use of to provide various forecasts. And in the end, also, I would like to dwell upon a little bit that what actually the meteorologists would need, what kind of satellites information would be necessary. So this is what I will try to cover in 30-35 minutes or so. So we'll have some time for question and answers. Next. Now, as I told you, basically all this, it is, you may be predicting weather for India or a particular region, but the most models today take the data from a global. And that is the reason, because the weather and climate is linked to the, whatever the energy and mass exchange is happening within one particular component within the atmosphere or between the different components, such as atmosphere and ocean, or atmosphere and biosphere, or atmosphere and land surface, or snow and ice, or between others. So this kind of a self-regulating, interconnected Earth system provides all information which could be from a global to the local scale. And that is what we try to understand and model for predictions. Now, we started with the ground observations way back in last century, and then the aircraft, and now the satellite measurements. And these are improving day by day. So basically, how the observations are very critical for the prediction is what I'd like you to say. So these are some of the kind of observations. I'm not going to show you, but this is people who may not be from this background trying to show some of the instruments, how they are being measured. Also from ocean, how the buoys look like. These are the huge buoys which is made mood buoys to make the various measurements of the atmosphere and some part of the ocean, upper ocean as well. Then the radio sonde and the drop sonde to measure the profiles of the temperature, humidity, wind. Then, of course, the reports from the aircrafts, and then the radars, which is very important, and of course the weather satellite, and which provides you the global coverage. Even first application satellite was the weather satellite. It was an intervened for quite long series, and today also there are many weather satellites, including INSAT, which has a long series and continuously provide the data. Now, if you see the ground measurements, you can see that there are several gaps, especially in the parts of Africa, many parts of the ocean. Practically, the observations are nil on Antarctica and Arctic. So you get some places a very huge concentration of their measurements, like you can see Europe and US, but there are many areas where the observations are very less. The radio sonde, which is one of the most important things, which also you can see that it's very scarce, except Africa is not there, ocean practically nil. Canada also, large part, it is not available. So there are large gaps. And then you have the aircraft measurements. Of course, these measurements you will get wherever the commercial flights are going, but that also provides a lot of observation which is being used in the forecast. But you can see in all this that there are large number of gaps. And the satellites, after they came, they filled up the gaps because they provide data from entire surface of the globe. So you get the information for each and every point depending upon the spatial resolution. Now, we have two major types of satellites. One is a low Earth orbit satellite, which is typically known as the LEO, which provide the high resolution data of the sea and land surface. It could provide you sea surface temperature, winds, salinity, soil moisture, many other things. But essentially, the spatial resolution is high, but it has a low temporal resolution. That means the satellite will come after 10 days, 15 days. If it is in inclined orbit, it can come after a few days. But essentially, it doesn't look at the surface continuously. While the geosynchronous satellites looks at the particular 1/3 of the globe continuously, and now they can provide you information at every 15 minutes if you put two satellites, like what we have done inside 3D and 3DR, but the resolution will be poor. So what is ideally done by the weather forecaster is they have a very good mix of both the low Earth orbit satellite data and the geosynchronous satellite data to take advantage of both the high spatial resolution as well as the high temporal resolution. Now, if you see currently the kind of a satellite data which LCMRWF is assimilating is almost 450 GB per day. And you can see that the data is coming from a variety of areas. It comes from all agencies like weather agencies like NOAA, from Korea, from China, from Europe, as well as ISRO, and the other data also is coming from the weather radars and the GTS, which is essentially a ground-based data. So you can see that the large portion of the data is today coming is from the satellite. Now, this is the same thing, but slightly in a different way. There are different kinds of a satellite and the observation. And you can see that the satellite wind is one of the most important things, which is also comes from the geostationary satellites, as well as the low orbiting satellites, and also the scatterometer winds. Then the satellite radiance is also coming from INSAT, as well as many other satellites like NSU, which is essentially a temperature, which is one of the major impact which is being made on today. And then now this, the RO, or the using the navigation satellites is also gaining ground, and this also provides a very high resolution profile. So apart from that, there are surface and all these informations, if you put together, you can see that and put into different models. I will not go into the details, you know much better, but there are different models and different resolutions, different purposes, and all this information goes in some or other way assimilated into these models. Now, today, if you see as we are seeing that almost 95% of the data which is going to model is from satellite. So it is very, very critical for all weather prediction models. Now, if you see Indian scenario today, is 3D and 3DR provide the global coverage every 15 minutes, which is something very, very useful, especially when we are tracking some of the features like cyclones or a cloud movement or storms or a dust storm. It is extremely useful when you have the data every 15 minutes. Also, the visible and infrared channels provide various information on humidity. Of course, this is not that simple. It has to go through various algorithms. Each of them has typical retrieval systems, and there are many other complications, but I won't go into the details. But these are the various information, and it's very useful for short range and the nowcasting. Of course, there are sometimes the radar images are also used, and the nowcasting is mostly based on the radar and the satellite images. The winds are scatterometer winds, which is essentially ocean surface winds, which are very important, and the atmospheric motion vectors, which is derived from both geostationary as well as the polar orbiting satellites, are also very important. The other important thing is the sea surface temperature, and this is now at a high resolution provided by INSAT. Only problem with this is that during cloudy conditions, they don't provide the information. So for that, we need information from the microwave radiometers. And these are one of the most critical information which is used for couple ocean atmosphere models for both subseasonal and the seasonal prediction. So you can see that from very shortly nowcasting to the seasonal forecast, the satellite data is become vital. I mean, today, without satellite data, no forecast is possible. This is some of the products which is generated, which is otherwise very difficult, like soil moisture, which is one of the very important parameter in NWP, but direct information on the regional scale is not available. So this is generated from the satellite-based data. Similarly, about snow cover, this is another very important parameter, is also generated from the satellite and then used for various systems. So there are many such products. I just want to show you some of the very important for which the getting information from the conventional means is practically impossible. So here the satellite data has made a major impact on the weather applications. And you can see that over a period of time, the improvement has come. Of course, this improvement has many reasons, but basically the augmentation of observing system, both ground-based and all, plus satellite and radar. And the assimilation of this into numerical models using high-performance computing. These are the two main reasons for improvement in our forecast, which we have seen in last decade or so. Like onset of monsoon now, if you see last several years, it is right on the dot. And that is essentially because the major information is taken from the satellite. And this, they have been able to monitor, and you can see that the improvement of the onset is very much accurate. And this has a lot of implications because a lot of issues related to sowing and this depends on when the onset of monsoon is. So this is one area where satellite has made a very major impact. Other major impact is on the rainfall estimations. So variety of the information is used from INSAT and many other satellites. And that rainfall potential is being found out. And the use is what we call it from a hydroestimator rain from an INSAT 3D, which is now being provided regularly for a variety of applications. And it is also used very successfully to find the heavy rainfall events even in mountainous regions. The other development which has taken place about the data assimilation has also helped. The 4D WAV, which is now very standardized, it has improved the various prediction of the temperature, humidity, and winds. And another sensor which was on the Safir with a sounder, microwave sounder, which was on the megacopy, the variety of studies which has done has proved that it is extremely useful. Unfortunately, this Safir is not being flown again, but this is one sensor which I think required very vital for the various applications, including rainfall and cyclone. I will show you one or two examples of that. This is the kind of a product which is now IMD is been generating a daily rainfall, which is of course a mix of both observer and satellite. And this is extremely useful for various stakeholders, including for the flood forecasting, water management, irrigation. And they are pretty accurate now because it uses over a period of time, the calibration of satellite data is also drastically improved. And it provides a very good information about what is the rainfall. And this is also used for ultimately for the various drought and other predictions. This is one which was generated a lot of controversy at that time. So I would like to show that IMD did provide the forecast well in advance about Kedarnath. And this is another important thing, that providing accurate forecast is not enough. It is also the response to that forecast, what action is being taken, and the people who are, how conscious they are to the forecast. Because this, I personally observed that though the forecast was given, the authorities did not take it seriously. The people also, in some places, it was also announced by loudspeaker and everything, but people also thought that this kind of forecast will not work. But it did happen exactly as it was predicted. So, and this was possible because there was high input from the satellite continuously coming, and they were very confident that it is likely to happen. So, this is one area where I think now after this, people are a little bit more conscious of the forecast given by IMD. And now they agree, I mean, they agree to whatever suggestions made, whether evacuation or whatever for the forecast given. And this is not one isolated event. All such heavy rainfall events, which happened in Gujarat, was also very well predicted. Then also the Jammu and Kashmir was also very well predicted. So there are a number of the Kerala and many others were predicted very well. And now the very fine application has come because the improvement in the rainfall forecast. What has been done now is to use this information and convert into how much area is likely to be inundated. The system has been developed after the Chennai floods, and it was developed by IIT Bombay with the close cooperation of NCMRWF, IMD, and then this system has been operationalized as a national coastal center for coastal research in Chennai. And now, because of this, all the information which is coming on the rainfall, as well as certain information coming from inquiries about the tide, the entire model for Chennai, and I understand a similar model for Mumbai also has been done. And here, for 3D, the other satellite data has been used, Cartosat, and then now it is possible to provide input ward-wise that how much area is likely to be inundated. So when your forecast is very reliable, timely, and accurate, it can translate into many such applications, which is extremely useful to respond to any of such hazards. Similarly, for drought also, where the first information is about the rainfall, which is coming from IMD, and then about what is the vegetation conditions, which is also coming from the satellite. Also, how much area is sown, that is also coming from the satellites, and the soil moisture. All these 4 different information which is coming from satellite is now used to give assessment of the drought. So this kind of a use of the satellite data has been extremely useful for a variety of applications like floods and droughts. Also, some of the examples of a fog is now satellite data is routinely used. Both INSAT and MODIS, both geosynchronous and low orbiting satellites, the thunderstorms, dust storms, and of course cyclone. I will take a little bit more time on the cyclone. The major input which is coming from cyclone, all the heat potential, what is the depth of 26 degrees centigrade temperature, sea level related issues, and SST. All these information coming from satellite is assimilated into a model. And that is why now our forecast of the cyclone has been extremely good. And it also provides the total extent, location, where is the track, where the landfall is likely to be done, what is the size of eye, what is its intensity. All these information is now being able to provide. And that is something which IMD has done now with taking all the input. The accuracy is so good, it's almost a 40 kilometer. Normally your eye itself would be 30-40 kilometer size. So it is very pinpoint accuracy which is now been possible. And because of this, the response of government has improved and the people also believe in this forecast. And that is where the lot of lives are being saved now, which used to be, thousands of people used to die, say 20 years back. Now today hardly anybody dies, except those who don't listen to them. Maybe 10, 12, 20, very small number of people still is being lost. It's mainly because they are not aware or they don't follow the instruction given by the local administration. Now, in this, also the Safir has been found to be extremely useful. To further improve upon the accuracy, some of the experiment which was done for the cyclone, especially Nilam, are found to be extremely useful. So this is the example of how the Safir data, when assimilated for the Nilam, it provided all these information in better manner than without assimilating the Safir. So they did a lot of sensitivity experiment with Safir and without Safir, and it was found that Safir definitely made a major impact on the understanding of the cyclone. Along with cyclone, also the information is provided about research, and you can see that this information also uses a lot of satellite data into their models, and the accuracy is pretty good about the surge predictions and the likely inundation. Also, the highways, which is predicted to be good, it's pretty good. The error is about 10% or so, 5 to 10%, which is quite acceptable. And the information about the currents and the waves, both are provided during the cyclone. So it is the complete information where the landfall is going to be, which are the areas are to be inundated, what is likely to happen in the ocean. So complete information when the cyclone comes is now available. So you are able to save lives not only the land, but the ships and the fishermen who are on the sea also can be guided where they should be going when the cyclone comes. Now, there are also similarly, like in ocean also, the wave, SST and the other things are primarily depend on the satellite, mainly altimeter. Like on the weather, it is mainly scatterometer and the sounders and the infrared and visible images. On the ocean, main is the altimeter. This is the prime sensor which provides a lot of information on the height, and this is now assimilated into various models to provide a global ocean state forecast. And this is for the regional, for islands, all and the particular location specific, about 100 locations specific also is provided about the waves, currents, mixed layer depth, and sea surface temperature. So which is very important for a variety of the applications of the fishermen, the navy, coast guards, the shipping. All these applications now depend on this, and the major thing comes from the satellite. Now, the two things which has made a major change in last decade or so is all the vertical profiles which we are able to give on temperature and humidity, especially the 19-channel infrared sounders on both INSAT 3D and 3DR are now providing the information profile of temperature, humidity, water vapor, and ozone. And this has made a very positive impact. The other development which is very important is the hyperspectral infrared, which could have almost 8,000 different channels. And of course, the processing is quite complex, but this is another area which we need to explore to find out about the hydrodynamics of atmosphere, which could be very useful for our predictions. The microwave sounders also are available, and the advantage is they provide data in cloudy conditions also, unlike the infrared sounders, which do not provide information within the cloudy conditions. As I told you here also that their resolution, spatial resolution is lower than the infrared sounders, but the accuracy is more. I mean, it's more reliable for the humidity and temperature. And the Safir again has provided extremely good data on these aspects. And the new sounding technique, what we call as the radio occultation or RO, which uses the global satellites, GNSS like GPS of US or NAVIC, and these all provide a very high resolution profiles. Of course, the processing is quite complex, and in all places this is not being done. But I think this has to be done because it provides very, very accurate, and even at every 100-meter interval you can get the information. So very precise information it can provide, and something almost like a radio sound it can provide you the information. Next. Another important thing is the wind, especially our tropical countries like India and surroundings. The wind is most critical, unlike the temperature in the western and the coast countries. So this is now basically we used to get through radio sonde, but we used to get once or twice at the day. Now satellite provides you globally and at a very high temporal resolution. So this is one which is very important. The scatterometer is now provided you on the ocean, and the assimilation of both INSAT atmosphere motion vectors and the scatterometer. We have our own scatterometer, OceanSat and OSCAT, and then SCATSAT. So both are the assimilation has found to be very positive impact on this. There are now new thing which is coming up is laser-based instrument Aladdin, which provide you the atmospheric wind up to 30 kilometers with every 100 meters. And this is very accurate. This is an area where further research and how exactly this data could be used. The other is the Cyclone Global Navigation Satellite System, which is also very useful because this is a microwave L-band, so it penetrates all the clouds and especially provides the information about the core of the satellites, what is the high speed winds there, and this is also very useful, how the cyclone is going to intensify or decay. So the wind observations are going to be very, very critical, and in future I think we need to concentrate on the laser-based instruments and this kind of radar-based instruments to provide the better information about the wind. Now, the important thing which we need to do, and since all of you are one way or other way involved in this, I think we need to evaluate how the satellite data assimilation has been done. We need to see each observation by observation, how exactly it is being useful. Because what has been generally observed, that the wind observation has the large impact. Then the properties of mass, like temperature, humidity, pressure. So the wind observations are going to be very critical for our all short-term forecast. The other which is making major impact is the radio sound. So we need a similar kind of an observation from satellite. Though radio sound observations are few, but they make a very huge impact. And that is why it is continued for all times, for as many places as possible. The third is the winds, as I told you, from GPS RO. These are the third most important thing. And then the temperature and humidity profile from the both infrared and microwave sounders, ocean surface winds, both from microwave radiometers, and then hyperspectral. I think these are the major areas where we need to see that how exactly the satellite observations are improving. Because in our kind of a situation, I think we need a lot more sensitivity analysis to understand that what is the actual role of the satellite data. The reason for this is that based on these studies, we can demand that what kind of information or what kind of sensor satellites we need in the future. So basically, this is kind of a lot of analytics which we do, observations, which is we help to find out and understand various phenomena, we assimilate this information, and then we model it, and then we use for the various decision-making, forecast, and application. So any improvement if we have to do, I think the improvement we have to continuously do on the observation. That doesn't mean that we don't have to improve our simulation and modeling techniques or understanding of the physics, but I think the observations are going to be key to improve everything. So with this, I would like to conclude. The most important thing is that the continuity of this satellite data at the frequency at which we need and accessibility is very critical. That means now you are dependent, let's say, on INSAT. There has to be ensured continuity of the INSAT data or say scatterometer or whatever information. Like today we are dependent on INSAT, both imager and sounders for a variety of applications. Then SCAT for atmosphere wind, which is very critical for ocean couple modeling. The altimeters or altimeter kind of sensors for water level, sea level, ocean modeling, and then navigation satellites, which is going to be very important both for temperature and humidity profile, and Cartosat for topography. The another satellite which was to be launched, somehow it was not launched in March. That is called GSAT, which is a very high spatial resolution, temporal resolution, which could be extremely useful for the weather prediction. So I hope that it will be launched soon, then we will be able to see what impact it could make. Now, this capability of this, we should have a national system. Actually, I would request, since Mahapatra is here, to design a national system for the weather forecast. What all is needed? What is the kind of a sensor you need? What kind of accuracy you need? What kind of frequency? What kind of spatial temporal resolution you need? And I think we need to do and provide that so that it can come. Now, some of the new thing which is also we need to put a request to ISRO. One is the satellite-based wind profiler. I think this is very important that the research can begin on this, and sooner or later we should be able to launch our own wind profiler. Second is microwave radiometer. I think we launched, actually India started with radiometer. Bhaskara 1 and 2 has a radiometer. Then we had OceanSat 1 radiometer, and Megatropic has a radiometer, but somehow it is not being followed up or continued. I think we need to come up with a very specific request to ISRO that I think the micro radiometer is made a very, very important impact, considering severe kind of radiometer. And also the sea surface temperature during the monsoon, we don't get from infrared thermal images. And a sensor, radiometer somewhere operating in 5 or 10 gigahertz would provide you very accurate sea surface temperature. So this is another. The third, we also have to say that the scatterometer, say wind or altimeter data is needed every 6 hours, because I understand you run model every 6 hours. So you need data every 6 hours. So if you launch one satellite, it may not have. So you may have to launch 7, 8, or 9 satellites to provide coverage at every 6 hourly. So that also we should design and justify that why it would be important. The other, which is I think is very critical, is that INSAT data is now available for last 35 years. And it has a lot of data which could be used to detect the climate signal. Especially two areas which I think is very critical is the snow cover and the clouds. We can see any trend in changing pattern in snow cover or a cloud. There may be a lot of calibration required because the sensor has changed from 84 onwards to today. But I think that it is possible. And I recollect the one small study done by Goswami and his colleague to see the clouds for not entire 30 years period, but for a few years, if I remember correctly, about 10 years or so, and they found very useful information coming out. But it's a very huge effort. It's a huge effort, and I think that it's a worth. And in future, we must try to calibrate data from one sensor to the other sensor. We don't have any calibration sites for satellite. I think this is one area which we need to see very carefully. And when you move from one sensor to the other, and it's a 3D to 4, 5, I think we need to go on calibrating so that the data set which we will have as a climate quality data can be generated out. Currently, we are using for one use, and after that, we think it is of not much use. But I think as the time passes, we would need to know more about how our climate is changing. So I think this one area which is very, very critical, and I request IMS to take it up very seriously, this aspect. And of course, the various technologies which we have been developing. I think we also have to have some system by transferring to industry so that it becomes a very operational system. With this, I'm extremely grateful for giving me this opportunity, and thank you very much. Thank you.
Thank you very much, sir, for a very wonderful talk. Particularly, you have highlighted the different prospects of how this ISRO with space-based data can be utilized for various applications in weather forecasting, and already in IMD and other agency in modeling study also, the huge amount of the satellite data are assimilated, and on day-to-day forecastings from short range, starting from short range to even from climate scale, all type of studies, satellite data are being used. But at the last slide, what you have highlighted that is very important. Means now a new sensor we have to develop or improve weather predictions, and also the satellite wind-based profiler, radiometer, microwave radiometer, and the low elevation orbit satellites, spectrometer, altimeter. So these all things are required for our weather forecasting, and even for already we are having collaboration with many agencies, ISRO and the nicest product we have already seen. They are also doing the lightning detection. This also we are using, but more and more collaborations are needed. And finally, you have also told that 30 years satellite data now available. Means the satellite data available for 19 after satellite era started. We have a good long series of satellite data available. So some climate change study also, that what you have highlighted, that also can be taken up using the satellite data. And the lastly, you highlighted that means the technology by that means industry. So that once it is implemented already, just in other sector it is already done, but we have not yet explored in our weather forecasting sectors. So in that participation will certainly help, and in future definitely this will come, and artificial intelligence, all other techniques are there. So that also tool will be utilized for satellite data and advancement of weather and forecasting. And sir, nice talk, sir, and thank you very much for spending your valuable time from your busy schedule, and we are very grateful to that you for such a nice talk. Thank you very much, sir. Over to Raju, sir, for your comments.
No, it is a wonderful talk listening to Dr. Sailesh Naikji. The only thing is, I always fascinated to have this type of instrumentation and collection of the data. Like when he was there at NCOIS, they also collect a lot of data for that forecasting, no tsunami forecasting. It is world over renowned because of the way it is done and professionally. And what I wanted is some point like any instrumentation which is done related to weather and climate. It should be through MOES. Anybody does so that information should go to MOES. You should maintain a overall dashboard portal. Either it is a state government or it is a central government or ISRO, DOS, because everybody does their own way. And finally, it is not going into your own models. And so that when it goes with all this information, real-time information, really that forecasting improvements can be enormous. But we have our own like MOSDAC we maintain, and IMD also maintain their own, and state governments and some World Bank funded information. So various things we also do for Disaster Management Authority. So all this, it is all government money and institutional money, but there should be some policy guidelines from the government of India level, and I think MOES should coordinate and come out with something. Should make this all mandatory to go to the centralized place, so that it can be used for operational forecasting and modeling, as well as for research purposes for researchers. So I wanted maybe views from Dr. Sailesh Naik also on this.
Yeah, I mean, there are two things. A lot of people may collect the data, but when the data is to be used in models, it has to be calibrated data. And the major challenge is if you have thousands of instruments, to calibrate them to a single, it may be good for the local conditions, but when you want to use, unless it is a calibrated data, it doesn't make much sense. So whatever my understanding is that they would prefer less number of data, but more accurate data. And that if it is supported by the satellite data, then you can, use this kind of information much better than all the data to collect at one place, because it is little difficult also, and the past attempts also have not really fructified to do that. So what I would suggest is that the best thing is that there are certain protocols and standards to be followed when you collect the ground-based information. Similarly, when you use, say, aircraft or even satellite, we must have certain standards and calibration protocols before we use the data. And so that when you use from, say, set 2 to 3 or 3 to 4 or 4 to 5, the accuracy is maintained. And that is why the calibration sites are very important for us to plan. And I think unless and until that is there, what will happen that the data value, as you said, it should have a perpetual value. It should not be used only for once. Now, to convert data for a perpetual value, we need certain standards and calibration protocols. I think it could be a satellite or a ground-based or any data. So that, while ground-based, there is a recent procedure and it is being followed. For satellite, I think we are not following. So I would suggest that is what we need. Some attempts were made to create a site in Lunark or something, but I don't think it is. So I think that would be one which should be done. then only we could be able to put everything.
I agree with your views, sir. I think it has calibration is very important. Yes.
Sir, one more point just I was thinking. And recently that inside 3D, 3DR, we have seen imager and profiler. But imager data are used for all applications. But the profiler data actually we have, but it is very limited. We have not explored whether it is because of the quality or whether it due to other thing. The profiler data are not extensively used. So how that case should be improved in future? That is, I think, a point.
Yeah, I agree. That is why, I showed that profiler data. Afterwards, I showed some examples of how the forecast has been done and that. I am aware that it is not. That I think it need to be investigated. My understanding is that there is certain issues about quality as well and the accuracy. So when you try to assimilate, it doesn't accept all the information. That is one thing. But this will happen only if we continuously try to find out what are the issues, and dedicated efforts are required to see, because you get this kind of information from now variety of things. You also have not Indian, but other microwave sounders from outside India. You also have a RO-based information. You also have so somewhere we need to use this information and try to calibrate, and sensitivity analysis should be done. How does this data is making a difference or not? Because if it is not making a difference, we should say that it is not of much use. But we are not able to say whether it is making difference or not. Overall, the global experience is that the profile data is extremely useful. Both humidity, temperature, and if you get wind, it is definitely much more useful. Because that is what you try to get from the radio sound. So it is useful, but the quality of the data, I think, has to be ensured. And that job is not only from ISRO, but I think both NCMRWF and IMD has to look at that data seriously, that what is that in that data? What are the issues? Why we are not getting, whether the algorithms are not, retrieval algorithm is a problem, or what are the issues? And I think it can be resolved. It's not that, see, even sea surface temperature, when today everybody uses just like that. But once upon a time, when it started, people had a lot of doubts. And the huge calibration exercise used to be undertaken. Even India took a huge exercise, almost 40,000 observations were made. And then we tried to understand what is some bias for that. And over a period of time, the algorithms were put. And today, satellite assisted, nobody doubts. Everybody takes it as a very accurate. So the efforts are required, I think, both from our side and the ISRO side jointly.
You are muted, Patnaik.
Yeah, so sorry, that is the right thing to conclude. May say ISRO side some efforts, and from our modeling side to weather forecast IMD and CNLF to resolve that thing, so that more and more the profiler data can be used both in the model as well as for the study, observational studies. Thank you, sir. Thank you very much, sir, for your nice talk, and also to our and Raju sir team for nicely conducting this part. Thank you, sir.
Thank you. Thank you very much.
Namaskar, sir. We have any announcement for the tomorrow and thing, then you can, this is a common platform, you can make it.
Yeah, Patnaik, you be now live. Let us discuss.
It will go to, I think, just to be. They going to go to website and everything.
Oh, okay. Yeah. Maybe you can come out here. We'll discuss separately.
Yeah, because it is. This is YouTube live. No, we should come out.
Yeah, it should come out.
So maybe just a common announcement means anyway today's program is over. And we, as per the summary program, there was a meeting with IMS local chapters. But since yesterday this aspect was already covered, so probably you are not holding it again. So today it ends, and tomorrow again our session starts at 10 a.m. And we have the last plenary session tomorrow, where we have three honorable speakers: Dr. V.K. Dadwal, Dr. Akhilesh Gupta, and Dr. Kalachad Sain, followed by last two technical sessions. And then after that, we will have a very special lecture by Dr. Elena Manukova, who is the Deputy Secretary General of World Meteorological Organization. So everybody should listen to this talk. And this will be followed by the valedictory program. So a draft valedictory program is getting prepared. Probably we will share the valedictory program also, valedictory program schedule in the portal by tomorrow morning. Because as a valedictory program here, we cannot bring all as to participate through video. So people can give feedback through the portal. But to few selected, up to 100 people will be invited to participate through video, and they'll be able to give their feedback online live orally. So thank you for today.
Yeah, for tomorrow, I think, yeah, we can discuss that thing.
Yeah, we will discuss separately, I think.
I think we'll stop this meeting.
Yeah.
Yeah.
Yeah. You let us, I'll connect by phone, no? I think.
Phone or Google Meet, you just connect. I am sending a link otherwise.
You send the link.
Okay, fine.